sure nobody is giving online presentation. We are so happy to have you as a session chair. Welcome to this. And we are starting with the first presentation on to India campus. Welcome to the session. I understand it is late evening now, and yesterday also you had full night working, which is absolutely amazing. Right. So we are starting with the first presentation. Over to you, Istvan.
Thanks. Good morning, everybody. I appreciate that you are here. Thanks for your time. Thanks for the opportunity that you gave me. My work is titled EMG-based control of a mobile robot for upper limb rehabilitation. So we are going to talk about electromyography. My name is Esteban Mora. I am from Ecuador, and the authors who work in this paper are Gilberto Perez, Mateo Sarmiento, Lucia Seas, and I. There are two universities who were working on this, Universidad de la SUAY and Universidad de Cuenca, both of my home city. So, what was the background of the problem? The lack of motivation in therapy. When you have an injury, for example, in the shoulder, you have to be in front of a wall doing this movement. Okay? So, what we are trying to do is to make it more engagement for the patient to do physical therapy. So, we are trying to implement some serious things. What was the motivation? To recover the impact of the motivation of the patient. And the research gap was most of the papers, most of the works are focused in qualitative assessment. But we are trying to give in this work quantitative because it's going to be more precise for the diagnosis. So, in the literature, we have worked in these two papers. The first one was talking about the interface between robots and humans. But in the first one, they used only a bracelet for EMG acquisition. And in the second one is also about the motivation of the patients to the process of the recovery. So here in the second paper, they say that there is not there is like 70% of people who stays in the whole process of the rehabilitation. So that's why we were implementing the serious thing. The methodology that we use is the next. So first, we have the acquisition of the EMG signals on 4 muscles. Then we have an interface between the EMG signals and the rod. This is a mobile robot. What we use is ROS. ROS is the robotic operative system, which is used for the universal robotic community. And then with different contractions of the muscles, the robot is going to be forward, backward, from left, or from right. Okay? Here you have the muscle that we use. We use to be intuitive for the movement of the robot and the contraction that we make. We have 4 muscles. The first one is the middle deltoid, which turns right. So when you do this movement, the robot is going to turn right. The second muscle is biceps. So when you do the contraction of the biceps, the robot is going to be forward, is going to move forward. And then the third muscle is the pronator, which turns left. When you do this, it turns left. And finally, the last muscle is the brachioradialis, which moves backwards. So if you want the robot to be or to move forward, you have to make a contraction biceps to go backwards in the brachioradialis, to turn right, the middle deltoid, and to turn left, pronator. For the processing of the EMG signal, this is the raw signal. Then we only work with the positive signal. So we make a rectification. But if we work only with the rectified signal, we are going to have problems because this is going to be like movement and not movement. So we did an envelope of the signal and we work with a threshold. To normalize the movement and the interface between the robot and the human, we work with the maximum voluntary contraction, the MVC. Why we use this? Because with my level of contraction, it's not going to be the same level of the contraction of other persons. So, in the experiment, we first take the MVC of each test subject, and then we work with the robot. The experiment is about moving the robot, but we took two groups, an experimental group and a control group. Both of the groups included 10 people. Okay? 5 men and 5 women. And also both of the groups have 5 left-handed and 5 right-handed. The methodology used in the experimental group was 3 tries of a round trip, okay, a round trip of the road with a predefined trajectory. So the robot has to complete the forward trajectory and then go back. So that's the round trip. And the 3 tries are first made with the dominant limb and then with the non-dominant limb. So we want to experiment if there is a brain learning about the motor of let's say, if the brain can assess the motor learning that exists between the opposite limbs. And the control groups only make this experiment 2 trials with a non-dominant limb. In the data collection, you are going to see this. We have the 3 trajectories of the experimental group in the outward trajectory and the return trajectory. So you can see in different colors how is the progress of each trajectory. And I ask you to see the first trajectory, which is blue, and the third trajectory, which is green. You can see that the green trajectory is like more clean. That's why what we saw is that in the first trajectories, the user is like struggling and trying to learn which is the contraction that has to be used. And you have the same in the return trajectory. So each one has 3 repetitions in the experimental group. Let me see if, okay. I hope you can see, yeah. I have a video, I hope it works. Oh, sorry. No, didn't work, sorry. But here we have the 4 muscles evidence of how were they working. You have first the biceps, brachioradialis, and the pronator, and the middle deltoid. If you see in this graphic, the most activation is made by the biceps, and here in the second image you have the brachioradialis, which is activated in the whole time. So now we can find which one was for the outward trajectory and which one was for the return. As we said, the bicep makes the road go forward. So this one is for the outward trajectory, and this one, which the brachioradialis was for the return, is made more in this the robot is going forward, is the only the biceps is activated, but the radialis is not. And the reverse, when the robot was returning, here we have the bicep who is not working, and the radialis is working all the time. What we found, the brain learns after you train someone. So here you can see the mean time that we have in each of the trials, in each repetition. So look, with the outward time and the return time. Okay, you can see how the mean time is improving because is in each repetition is less than the other. Okay. Then we want to show you this in the experimental group, how are the graphs. The first one, the first repetition, first try with the dominant hand or with the dominant lead, we have in blue, so it travels a little bit. But then with the green trajectory, we can see that it's more clear, more clean. And with the non-dominant, you can see as well how it's clearer than the first one. What we wanted to see is if there was improvement in trajectory and improvement in time, doing from the dominant limb to the non-dominant limb. And this is what we find. We start with the first repetition in the dominant, and we compare it with the third repetition of the non-dominant. As you can see, in distance and in time, there is an improvement in outward trajectory and return trajectory. Finally, we made a comparison between the experimental group and the control group, taking into account that the experimental group worked with the two limbs and the control group only worked with the non-dominant. Okay, so we only compare the non-dominant limb. Okay, and we found that there is an improvement, and this improvement is better in the experimental group. As you can see, in trajectory is better, and in time is also better. Trajectory and time. Finally, we made a survey of how the users, how the test subjects took the experiment. So we asked them if if they felt some engagement about working with a robot who basically is a biofeedback of what they are doing and how the robot is moving. And we have the 90% of the people who were agreed. This survey was made just with a Likert scale. And about the robot obedience, the 55% of the people said that the robot was making the movements they tried to, and we have the 30%, they were totally agree. 55% they voted for 4 and 15% with 3. For the conclusions, we found that the human robot interaction was made it really good because the users were engaged with the movements, and every contraction was looked at the robot like biofeedback. About the results of the using the dominant limb against the non-dominant limb, we saw that it was an improvement in trajectory and time by training. The difference that we found here, we made some statistics analysis, and even though there is a difference between the experimental group and the control group, the statistically difference was not significant. So this means that we can try to do more repetitions to see if there is a significant difference. And finally, the engagement we found with the subject that was one of the objectives of the work, we can see that it was pretty good. As future scope, we propose to use wireless EMG sensors and use other devices for human-robot interaction, which we are now working on it too. I don't know if we have another video here, but I think it's not. Oh yeah, it worked. So this is what we're doing now. We are working with wireless EMG sensors, and we also are having this biofeedback or this feedback about my contractions and the robot contractions. Let me see if we can have the other video, because it is important for me that you see how this robot was working. Here. This was the experiment. So you can see the user doing the contractions and making the robot complete the transit. To finish this, we try to engage the patient with this therapy to make it complete the whole recovery process. And here are the references. Thanks for your attention. Do you have any question? I'm happy to answer.
I just had one question. So you mentioned in the next steps you want to leverage some wireless sensors.
Yeah.
So what are, like, have you already given a thought about, like, what are those EMG sensors?
Yeah. If I understood your question. Now we just bought we just buy this wireless sensor this year. Okay, because we were looking for this EMG system, but with wireless sensors, but they were like $15,000-$25,000. They don't have the budget. So we found this system, which is 8 sensors, and it is only $1,500, and they are working good. So that's the next step, because the wires also have noise in the signal. So now we are eliminating that.
Thanks. Oh,
Thank you. Thanks for the question. Okay, thank you. Thank you very much.
Thank you so much. Any question by India team? Okay. Next presentation, we move on to the next presentation. Which presentation? Is 243 here? That's your presentation?
Yeah.
Check. So next presentation is by Lakshmi Narasimha Krishnamurthy. Let's make it full screen.
So you have the options.
Let's do a function F5. Should it?
No. Slideshow. Yeah.
Just so, right. Straight. Can you check? Is the screen visible? India team?
Yeah, it is visible. Yeah, it's visible. Please change the slide just to see if it moves or not.
Just a second. Is it moving?
No, not moving. It is not moving.
What, he did something? What you did to he did something. Oh, it's moving. Is it moving?
Yeah, now moving. Now it's moving. Yeah.
Now it's moving.
It's moving. It's okay.
Did that thing?
Oh.
Moving.
Here you are in Zoom, and here you are in.
Screen.
Yeah. Yeah. That's. How to do it?
Scan so that it will get the notes in there.
Yeah.
Extend is there. Control. Things will come. I think. Yeah, let's go there. Okay, so this is your screen. So this is just move it like this. So this is your screen, okay? And then you can close this. Where is your PPT? Where is your PPT?
Being go
Here?
Yeah. I think there or in. Yeah.
This one, right?
Not
Here,
this
PPT?
one. Not this one. Not this one. Maybe in the. Yeah. Go here. Go here.
Yeah.
Go.
This one is
Yeah.
PPT here?
Yeah. Yeah. Here.
Okay. Then you have
So
to
better
give.
duplicate, no? So
Not
whatever
duplicate,
you
not
see here,
duplicate.
you see there. It's easy.
Extend. I want
Extend.
extend.
Where do you go for the slide zoom?
Here. Meetings.
Yeah, go there.
Ah.
Speaker notes. Yeah,
Okay.
on that. Yeah, you get it right.
Yeah. So only extend this.
No, I think.
Should I do?
Yeah. Right.
What is the issue?
1 second. So I can.
Yeah, drag it. Yeah.
Is it not coming? I'll do it.
Hmm.
Give me a minute. Give me.
Extend.
Yeah. Extend.
Let's go for duplicate.
Now, if you extend it right, you will see the notes here too.
Okay. Hmm.
Okay.
You cannot see the note. It's duplicated.
Yeah. I want extend one.
You just extend it. Go to the. What is this function?
Function F7.
So you extend.
Mm.
Click on that. Now you have to drag this right. Yeah. We have to drag this.
Yeah, drag there, yeah. Or maybe this side, yeah.
Side.
Yeah, yeah.
And now it's coming. You can. Okay, good, right?
Mm.
To the slides open.
Is coming?
It's the one, right?
Um,
Where is the slides coming? Yeah, here, right? Okay. Here you come. And then do with the.
It is already in slides.
Yeah.
No. You have to open this.
It is showing exit slide.
I'm telling you 1 minute. You can keep this
Yeah.
here. Okay. That's it.
Okay. So I'll go from.
Yeah, you can go one by one here.
Okay. Okay.
Good.
Yeah. Yeah. Yeah, it's working. Yeah,
Nice.
okay. Hey, can you hear me?
Yep.
Hello? Yeah.
Yeah, we can
Hello?
hear you. We can hear you. We can hear you.
Sorry to interrupt you. We cannot see your presentation. Am I audible?
Yeah.
I see your drive is open, but we cannot see your presentation.
Okay, Zoom.
What is the Zoom call?
Yeah.
Share screen.
Look, yes.
Oh,
Already
it's already
shared,
sharing.
but It is
No,
right.
share
Just
other screen.
stop sharing.
Stop sharing.
Stop sharing.
And then share.
Go share. And select your file.
This one.
Okay.
Yeah. Set the other window.
Can you see it now?
Yeah, now it's
Yes.
visible.
Can you move your slide for testing? Change your slide.
Change your slide, please. Move to the second or third slide. It's not moving actually.
No, you have to go to
That particular screen. Where is it?
the screen. Now you see.
Where is that screen?
You just want to show a slide, right?
Yeah.
Just one slide? So
No. It's like
You
it's
have
not
multiple
moving. No, multiple slides, but it's not moving.
You have just.
I suppose don't go on full screen for presentation mode.
Please.
Remove that presentation mode and
Just-
try.
Just a sec. Let's go the other way because that will not disturb me. Otherwise, it will disturb. Yeah.
Our laptops.
Yeah, that's the case. Yeah, that is.
Okay, 3 and 9.
Let me see.
Our laptops.
You can use your laptop. Why not?
Yeah.
I have Mac. Is that okay?
If
This
this
You have
HDMI.
HDMI connector?
Yeah, I think.
If you have
the-
connector, you can do that.
You can use that.
Let me first try. This is your presentation.
Yeah. Is it visible?
Is it visible now?
Yeah, visible.
We are changing the slide, right?
No, it's not changing.
It's changing.
It's changing.
Yeah, now it has changed. Yeah, changing.
No. Yeah.
Maybe you can on that. Huh? Can talk on that.
Yeah.
The notes as well? No? No, right?
No.
Yeah. Just talk.
I just want to see. It's like it's.
Just talk on.
Yeah, sure. Yeah, I have
Open it
this.
from there.
Yeah, I have this one also. So maybe this. Morning, everyone. So it's been like a long time that I've was okay. So I'm going to present deep learning driven emotion recognition using heart rate variability. So I am the presenter Lakshmi Narsimhan Krishnamurthy. I go by the name Narsi. And we have our co-authors from Amrutavahini College of Engineering. So this is a deep learning driven emotion recognition using HRV. And we are introducing that BLE GAT architecture here, Bluetooth Low Energy Generic Attribute Profile. So this framework is like real-time affective computing. So affective computing is like having emotions, like getting from your body and using sensor. So we are using that one and transferring through BLE, and we are verifying all those emotions. So this explores the leverage physiological signals to understand human emotions more accurately, so and effectively. So moving on to the next one. So this is okay. Okay, so this is the introduction, the power of physiological emotion recognition. So physiological emotion recognition offers a powerful and resilient way to understand human emotions. Say for example, we can fake few expressions but not our emotional expressions. And say for example, we can fake our facial expressions, we can fake our tone expressions but not our heartbeat. Few sensors like it takes from your pulse, so these ones, so you cannot fake it. So physiological signals are harder to fake, and this technology like BLE. So why we use BLE is like it's lightweight and it can like use less power, and uh, so collect data continuously. So it has like 98% accuracy. So using that, you can take all those sensors. I mean, you can data from your body. So we have nowadays sensors like continuous glucose monitoring, so that you have like a sensor here or maybe other parts of the body, but the accuracy is like here and on your thighs. So from these things, it's like you can take all those data from your body. So it's not like you have to like every time prick your finger and get blood and see the glucose. It's not like that. It is attached to your skin. So using that, you can get all those data from your body, transfer it using Bluetooth GET. So we are using that architecture, and what all the device that you have, that device is like getting it. Say for example, smartphone or a blood glucose level device. So all these things. So it can connect, it can get data continuously in real time. That brings us the challenges that we face in uh, current world. So physiological signals are like more resilient to deliberate manipulation that visible or visual or vocal methods, and the connectivity that you are using, as I said, BLE, the architecture is BLE GAT. Okay. So I'll come to the research gap in the current world that we are having these type of sensors and devices. So emotion recognition solution have significant limitations. Say for example, using modern machine learning relies on like hand engineering features. That means it generalizes across different people or situation. It faces like power or like scalability issues, especially monitoring 24/7. So that's one issue that we have. We don't have like enough power reserve using like a battery or a continuous power reserve. So but using BLE devices, the great example is like having like small batteries. So inside the device that you have, and it will transmit the BLE data continuous to your mobile device or whatever the device that we have. The signal quality is also a big hurdle. motion artifacts, wireless interference can easily corrupt the data. And the complexity of BLE, the Bluetooth Low Energy heart rate pulses, making makes data interoperability that real changes. So operability is we are getting devices, we are getting signals that can be transferred from one way or other, one medium to other, and one machine to other easily. So these gaps highlights the need for the more robust and intelligent approach, so that we are currently dealing with, and here we are going to see that. So the research objective, so here is we have four. One is proposed for an integrated framework for real-time emotion detection using wearable sensors. So as I said, the wearable sensors, what you have is a kind of you can have a ring type that you are using, like nowadays for gym goers, you are having a ring, or maybe you can have your phone attached, but every time you cannot have it. So you using your watch, so wearable watch. So the watch is also like a sensor. Underneath there is a smartwatch. The sensor you having it also measures your ECG, blood pressure. So it's not like just seeing for a time. And so we have all these technologies and sensors right now. So the second one is leverage the Bluetooth GATT protocol for efficient, low latency and low power data transfer. So as I said in the beginning, so using Bluetooth, it's 98% efficient. So 2% maybe here and there you can lose data packets. And so this one, the third one, we are implementing a hybrid CNN convoluted neural network and LSTM. So LSTM is long short-term model. So you are effectively capturing both spatial data and traditional machine learning models to demonstrate its enhanced accuracy and resilience. So we are having not using CNN, we are not using long short-term memory. We are combining these two. So using that, we are achieving this 98% accuracy. So next one is the technical foundation for this BLE GAT architecture. So this is our heart. So BLE GAT. And technical foundation is built on this architecture, which is crucial for effective data handling. So generic attribute profile. So GAT profile is data for clear hierarchy using services. And characteristics, say for example, heart rate monitoring and measurement, ensuring a standardized way to share physiological metrics. So physiological metrics is the pulse, heart rate, and visual, all these things, and the ensure standardized way to share optimized for low latency and power consumption. And more importantly, GAT secure transmission. So some people have this fear of losing our privacy data, our private data. Say for example, we are having the heart rate, we are having diabetes, and what if this data is exposed to the general public, or someone take this data and put it on a public. The BLE data is end-to-end encryption. So we are secure transmission using the BLE data to your device. And sometimes if you want to put our data in the backend, if you want to see a 90-day data, say for example, and everything will be in your account, and you can see it for the past 90 days, how much we are in stress, so how much we are undergoing all these negative emotions. So you can other people cannot see it. So that is one major advantage of having BLE GAT architecture. So this proposed so methodology. So what we are having is again we are having 4 stages here. In accusation, what we are having is real time acquiring this PPG. So PPG is photo plethysmography, and ECG signals. So ECG signals, as you know, it's for the heart and everything. So we are taking these signals, capturing from your wearable sensors. So it can be like any sensor. Using these sensor, we are transferring these data securely using the sensors to your phone or any other devices. And after getting these data, so we are pre-processing. So pre-processing is like using this bandpass filter and peak detection to isolate the clean RR intervals. So RR intervals is nothing but the signal that you get, like you see in ECG. So that the gap between these two peaks. So, and after that HVR extraction. So here what we are getting is using this HVR like heart rate variability. So standard deviation of NN and root mean square. So RMSSD. So these features in real time and frequency domains. So finally, the last one is like classification. The classification, what we are having is like using this hybrid CNN and long short-term memory. So as I said before, it's like a hybrid of these two things. So these two things using that model for emotional classification. So integrated pipeline as the key to moving from the raw data to that emotional states, that is set the stage for deep learning architecture that we'll see next. So this is the hybrid model that I was talking about. So building this methodology, let's explore this one and the convolution neural network, the CNN and the LSTM. So the architecture is specifically designed to capture both immediate and evolving patterns. So evolving patterns in the sense, say for example, in future, if you are like in this situation, you might get stress. So this is like, yeah, that is one. And we are leveraging CNN to extract the spatial feature and local patterns. And we are having that HVR signal segments, which helps identify instantaneous psychological changes. Then LSTM layers capture the long-term temporal dependencies and sequential trends. So it is crucial for getting all these data. That's why we are having a hybrid method. The synergy between these two layers allow our model to handle both instantaneous changes and sequential trends, significant for our classification accuracy. So also it is lightweight, suitable for like edge assistant computing and all the way transferring data without any data packet losses. And the other one that we are going to talk about, why we are having a hybrid method, why not CNN alone or why not LSTM alone. So the transmission rate, as I said, is 98%. So it having 2% of data loss, and the average latency is 120 milliseconds, which is like pretty accurate, which is good. And so the next one is like BLE GAT communication. So this communication is having 2%, as I said, 2% data loss, and power consumption is also low. This one is operated by like a small battery. So as I said, you can have it for a long time. Say for example, we have a Apple Watch, which like comes like for a whole day, and some other watches it comes like 3-4 days or like maybe a week, and that has like a small battery, and you don't have to care about for a week or maybe like more than that, and all these data transfer has been happened. So the findings. Overall system performance, the accuracy of emotions, that the happy emotions, like say for example, happiness and relaxation. So we are able to get it at an accuracy rate of 94% and 93.2% respectively. The other.
We have a time limit of 10 minutes per present. So if you
Okay, sure. I don't know that I'm like taking more than. So yeah, stress is 91.5%, demonstrating like hybrid model, and so the neutral feelings as well as like um, negative emotions, we are having 91% accuracy. So the next slide, we have that implications in the transforming healthcare and smart environments. So personalized healthcare with continuous monitoring emotional state, identifying stress, anxiety, and the smart environment is like emotion aware system can adapt lighting, temperature, and music to enhance your comfort level. So yeah, so this one is the implications, and then the conclusion. So we are overall 92.4% accurate. So but the happiness and the relaxation and the positive emotions, we are having accuracy around 94. And overall, like stress and everything included, the average is 92.4. So as usual, we are using BLE, so the power consumption is also low, and it's also real time, so you can see the real time data. So it is used in maybe you can the application is in so for people who are having stress, they are feeling stress, anxiety, and everything. So it will be used in medicinal field. So this is my conclusion, and yeah, if you have any questions, we can discuss.
I have a question. You mentioned that you calculate the age of the device.
Mhm.
There are some phone apps that give you the age of the. Do you think they have accuracy or not about the age?
So what we are seeing using personalized people. So we are using people for this data collection with their consent. So using those methods, we are not seeing like this much accuracy. Maybe because of it's like free app and all those things. So we are not seeing like 90% or more accuracy, but for positive emotions, we are seeing more than 90% accuracy, 94% and close to 93.5%. So that's why we are using this one. Thank you. Thank you.
Thank you. Going forward, if you can restrict it, let everybody know that they have a time limit of 10 minutes.
Let's follow the instruction by session chairs. The time limit is 10 minutes, 10 to 12 minutes. Please adhere to the time limits. Next presentation is by Venkatraman. Venkat, can you check? Are you here?
256.
365.
256.
Sorry.
Yeah, 256. 256. 256. 256.
Whose presentation is this?
Yes, Hassan.
Is it yours? Can we take his presentation first and then yours?
Sure.
He wants to go.
Yeah.
Thank you so much. There's a gentleman there.
Okay.
Thank you so much. Is this your presentation?
Yeah.
If you can check, are the slides visible?
The slides are,
Are
they are not moving.
Okay. Are you able to see full screen?
Yeah, full screen. Yeah, full screen. Yeah, moving now. Moving as well. Full screen and moving.
Thank you so much. Thank you so much. Over to you.
Hey guys, good morning. I am Venkat Ramani Medisetti. I'm based out of Raleigh, North Carolina. So I work as an infrastructure architect at Arch Capital Services. So today I'm going to talk about the paper Federated Learning with Explainable AI for Natural Language Processing in Large-Scale Distributed Systems. So we have co-authors Ramneet, Manish, Raghu, and Gurinder. Let me take you. So if you see currently there are in today's AI world, right? It's most powerful. AI systems are most powerful in medical, in healthcare, financial, and cybersecurity, and smart cities, right? So there are two major problems with the AI systems that we have, right? So the problem is these healthcare banking institutions, they cannot centrally share the data because of the privacy reasons, because they have the medical information and they cannot share the banking information to a central cloud server. So that's one of the problem, and the other problem is the AI systems operate as black boxes, which means that the AI makes the decisions, but the humans don't understand why the AI made the decision, right? That's another problem, right? So our research, it explains about both these problems and solve both problems using the federated learning and explainable AI. So the existing research on the federated learning shows that it preserves the data privacy because the data stays local and it is not being shared to any central server, right? This data stays on the local devices, like the mobile devices or the IoT devices or the local servers, and it is not being shared to a centralized cloud server. So, and the existing explainable AI techniques such as alignment, SHARP helps improve model transparency. And the federated learning and explainable AI integrates explainability into the federated learning systems. However, there are gaps with the existing framework, right? Because there is no evaluation of privacy, impact, or the efficacy of explanation and scalability together. There is no standard evaluation framework for that. And these many explainability methods are computationally expensive and difficult to run on the edge devices because the computation, there's an overhead on the computational compute on the edge devices because of the limited resources on the edge devices, right? And there is a difficulty balancing privacy with explanation quality. So like you see in the architectural right side, right? So our proposed framework, edge devices such as the mobile devices or the IoT devices or the local servers process the NLP data locally. Instead of sending the raw data to the cloud, only the model updates are being shared, as you can see from the architectural right? So we used techniques like SHARP, LIME, and BLIME for explainability. And we introduced three metrics for evaluation. One is the CCS, Computational Complexity Score. The other one is the privacy versus utility, and GLED, Global Local Expansion Divergence Technique. The computational complexity score evaluates the explainability on it evaluates the computational overhead on the edge devices when we generate the explanations. The global local expansion divergence, it measures the difference between the local explanations and the global federated models. Privacy versus utility, it measures the privacy, how the privacy preserving techniques impacts explanation quality. So the key findings from the research that the private federated learning protects sensitive data and the explainable techniques improve transparency and stakeholder trust by explaining the AI decisions. Our major contribution is the reduction of overhead on the edge devices using the lightweight explainability techniques. And the GLED global local expansion divergence helps identify inconsistencies and bias between the local and the global models. So the future AI systems cannot just focus on the accuracy, they must balance these three, like privacy, scalability, and explainability. So lightweight explainable techniques are essential for IoT and edge devices because of the limited resources on the edge devices, and there's very less compute power on the edge devices, right? So comparison with the previous studies, compared to the traditional AI systems, existing solutions focus on performance and prediction accuracy. However, the existing federated learning systems lack strong explainability. Our proposed framework integrates privacy, explainability, and scalability into one single architecture. Excuse me, so our findings indicate that the proposed scalable explainability AI framework preserves privacy without sharing the raw data. It only shares the model updates, and it also improves the transparency by explaining the why AI made certain decisions, right? So the humans can understand why AI has made the decision, right? And this work supports development of secure, explainable, and trustworthy AI systems for future distributed environments. So the future scope, the work should integrate advanced LLM-based explanations, and there is a lot of future potential for real-world deployment in smart infrastructure and large-scale IoT systems. While there is computational overhead still exists, further optimization should be required. And here are the references that I used. Any questions? Thank you.
Thank you so much. Next is 256. Thank you.
This was 365, right?
This was 365. What's your paper number?
Shashank.
And Shashank Bharat. Your meeting is over?
Not yet. It's here and there parking it.
If you want to finish it up and they want to.
No, I'll
Choice
get
is
it
yours
done,
then.
yeah, because I'm back to back.
So,
Yeah.
we have like a different present learning.
356. No.
256.
Okay, 256.
Yeah.
I'm putting it on screen. Just like.
Yeah. Actually, I'm the presenter.
Oh, okay.
So they put the name.
Wrong present learning. Okay.
Shashank Bharadwaj is written.
Yeah, I'm the presenter. I'm Shashank.
But on the sheet, other name is well.
Yeah, that's mine.
And both of you are authors.
Same author.
They both have. Are we good to go?
You can, I actually wrote it down also, right? I strike it.
It's
and
okay.
put it
It's
down.
okay. We'll check. No, no worries. No worries.
Please move the slide.
Just give me a second. Is it on full screen?
The full screen.
I'm changing the slide now.
Yeah, changing as well. Full screen and
And-
changing.
So, hi, good morning, everyone. I'm Shashank Bharadwaj. I would be presenting the agentic AI-based threat hunting for those autonomous security networks. Going on to the next. Yeah, let's discuss the problem here. So we know that, like, the modern day industries are working on multiple clouds or multiple IoT devices or different sort of control systems, all the consistency communicating with each other, right? So that's where, like, there is a huge scope where a new platform or a new possibility for an attacker to invade would rise. So let's talk about how was like the legacy IDS limitations which we had. So initially that was like a signature based detection and a rule based response systems. So basically what happened here was, like, it wasn't that enough to secure the identity. Like for example, if you're walking into an like a bar or like any pubs, you would actually see like bodyguards scanning for, like, ID proofs and stuff. So here is where, like, signature based detection actually fail, where it could only, like, provide the exact information but not on like, hiding the sensitive information. So then it also moved on to the machine learning models, where the traditional machine learning models were all based on the anomaly detection processes. But this improved the accuracy, but the main issue was that there was no, like, real time action, or, like, there was no real time capability to dynamically solve the problem. And another biggest challenge in the industry today is, like, centralization bottlenecks, right? We know that the systems are like, depending on the centralized response strategies. So that's where, like, we could see a very critical risk, where a single point of failure could actually bring down the whole system or the process itself. So moving on, how we addressed this, we started thinking on, like, why do we need an like, autonomous defense, basically, right? Here is the problem, right? In, like, real world scenarios, so cyber threats are way more faster. It's evolved so fast that, before maybe in the minutes, and today it's in the seconds. So even before, like, the those threats are, like, identified, analyzed, and taken the right action, already the attacker has broken the firewall. So that's where it opens up, where we need a system which could sense, which could reason, and also act simultaneously on a real time basis. So let's see what actually autonomous defense delivers, right? So initially this consists of a localized decision making. So basically it clusters the nearby data sources, which actually reduces the detention latencies. So it also contributes towards the collective intelligence across multiple agents, which could strengthen the global defense policies. And it is also very much like, adaptive when it comes to the reward engineering. So it balances, like, a security enforcement with service availability. So that's where, like, our main autonomous defense we focused on in bringing the sense, like, reason and the act. Moving on to how we saw the evolution moving through. So initially we saw it's all started from the early Q learning, where the initial reinforcement learning models actually applied the basic firewall like rules and certain intrusion responses. So there was a few gaps. That's where deep Q networks entered into the markets, where the DQN addressed the curse of dimensionality by approximating the value functions with deep neural networks, and which actually improved the IDS classifications of accuracy and the repeatabilities. So this also gave rise to another evolution of actor critic or the policy gradient. So here what happened is it focused on improving the convergence stability over the pure value based models. So in spite of all these, we still observed that it was a centralized system, and that's when another new system entered into the market of a multi-agent reinforcement modeling. So in the multi-reinforcement modeling, we also saw that this IQLs and MADDPH frameworks, they were demonstrating a good DDoS resilience through a shared state information, but still the synchronization mitigation across the distributed agents was a big challenge. That's where we observed that centralization was one of the major roadblock in the today's world. So that's where our act response actually came into the picture. So that's where CT, DDE and GNN integration, so basically where the graphical neural networks were used, where it was enabled with the topology sensitive informations which actually helped for decision making based on the profile of an attack. So moving on to the next, let's talk about the main gaps, the research gaps. So one of the main gaps we observed was the lack of integrated containment, recovery modeling. So basically, what happened was, so when an attack is actually detected and it's tried to mitigate it, but it was highly ignored of automated recovery. So and the service restoration was actually a challenge. So that's when it moved on to scalability limitations we observed. That's when many approaches, since it was a centralized, as I mentioned, we could not scale it with a large distributed systems. So the other research gap we also observed was there was a very limited adversarial robustness. That is nothing but the existing DRL models, right, could still remain vulnerable to multiple perturbations, and also it is very challenged to train the data against those poisoning profile of attacks. So that's when we also observe the lack of certain explainability, as also showed in the other PPTs, and also the trust mechanisms. So because the few methodologies, right, it definitely incorporated few interpretable a decision making, but it also required few compliance angle where the operational transparency was actually compromised. So moving on to the framework of this UMA RDRL. So basically the framework started with we would input certain traffic logs and stuff within the graph-based representing agent, where it would objectify as a certain graphical notations, and that's where it would be moving into the multi-agent policy coordination. So that's where the different policies would be set up, and it would move on to the containment and the recovery incentives. That's where it would contain and also make sure of the automated automated recoveries of the loss. So that's which that gave result to the robustness training, which also helped adversarial to production of the policies, where all our samples, a set of policies would actually put into the test and set few guardrails. So this is the step which is the network, the graph based state representation. So here is where the structural embedding happens, where there's the topology sensitive decisions and accurate lateral movement modeling across the complex enterprise topologies would be aligned.
was.
Oh, yeah. Thanks. To the constraint of time, I would move on to the autonomous policy output. That's where we actually observed the real time threat detection. That's where the topology aware detection of the APTs and also like the lateral movement and the DDoS were in the dynamic environments. And we also observed the coordinated containments with our model where the distributed agent could actually isolate themselves and could also build certain nodes which could prevent disruption of certain flow which could legitimate the traffic flows. So moving on to the results division. So basing on the results on the simulated data, we found that the signature based IDS closely achieved close to 85.4 like the detections and which was adequate for the known threats for the ineffective against any 0-day or multi-stage attacks. So we also observed like in a single agent DQN also improved by 91.8 and also like our model of UMA DRL which actually achieved a 97.9% in a detection rate, and it also auto recovery or the containment of 94.7% was enabled. So moving on to the interpreting the results. So as I mentioned, the representing the network topology as the dynamic result graph enabled the agent to capture the structural attack dependencies and the lateral movement patterns, and which also led to the joint the detection, containment, recovery optimizations, and outperformed other approaches, and which finally came up to the adversarial training, which reduces the operational false positive, almost 57% reduction in the false positive rate, which we were observed as compared to signature based IDS, which was partly attributable. So final conclusion was in our model started up with a detection accuracy of 97.9% with 52%, 52 second of the recovery time, with a false positive rate of 3.1 and with a downtime of a 3.9. Being on to the the future scope and limitation. One of the major limitation is, as I said, it is since it's it's a centralized architecture. There would be many other challenges, and also there is LLM augmented policy reasoning which could hallucinate and degenerate. So yeah, thank you for the time and take a more time.
But we can respect the time. We all please respect the time 5 minutes. As a researcher myself, it is very embarrassing if somebody holds you stop there. This is our emotional work, isn't it?
I know.
So, but we'll attempt 10 minutes. It happens. That's a very difficult time when we have to finish all the presentation on time, but at the same time, we have given our heart and soul to our research work, isn't it? So next?
237.
237.
Prashant, you already signed it? So, yeah. It's not. We have
Which one?
37. Last.
Yeah. The first one to reach here. This is your slide, right?
Yeah.
Are the slides visible?
Yes, ma'am. The slides are visible. Please make it full screen.
Yeah.
Click on this slide and then do.
You never know which trick works.
Yeah, full screen and moving as well. Full screen. Yeah, full screen and moving.
Over to you, sir.
Thank you.
So if you're requesting for photograph, I'm sharing photograph on WhatsApp group. If it's that WhatsApp group, what should we?
Hey, good morning, everyone. This is Selvaraj here, Selvaraj Dorairaj. I'm a senior technical architect working in Warren, New Jersey, working from Warren, New Jersey. I have my co-authors here, Vivek and Ilangovan, for this paper. So I'm going to talk about our paper titled as Dynamic Pluralistic Alignment, Value Alignment and Ethical Decision Making in Autonomous Agents. So we have the lot of autonomous agents developed, and we need to really need to know that how this is benefited for our community, as well as we cannot fully trust autonomous agents fully. There were a lot of constraints and ethical constraints involved in it, and we have to build highly capable autonomous agents with ethical concern into calculation. So that's what this is a paper about. Let me go to that one. So what is the rise of autonomous agents? Nowadays, we know that AI systems evolve rapidly from passive tools to autonomous AI agents. These agents are highly capable of, long-term horizon planning, goal formulation, and independent reasoning. These models are good in their boundaries to perform. Whereas if we go to the out of boundary, like out of distribution, the behavior and results will be, indifferent. So it may not intend the human intention. So we need to build this. We have to be very careful about these autonomous agents. These autonomous agents enter into the high risk domains such as healthcare and finance and defense. The alignment is an important concept, important thing. Not only the ethical concern, it is a technical necessity. So we are in a responsible situation where to build autonomous agents which will in line with our human intent. So why the value alignment is important? So the autonomous agents are highly performant. If they are not aligned properly, then it is dangerous to our entire system. Okay, so it's not good as like our fixed models. So we need to really careful about the alignment on the autonomous systems. So why there are a lot of risks because of these autonomous systems without having an alignment. For example, just a minute. So these autonomous has a lot of risk involved in it. Like the autonomous agents do their goal set and processing internally. This will not intend to our human outcomes. Also, like the ethical features, these several autonomous agents are mainly targeting the Western culture thing. We wanted to get the autonomous agents for global situation, global system. Okay. The case studies for the human aligned agentic AI, these methodologies like reinforcement learning from human feedback, constitutional AI and cooperative AI, and then multi-agent reinforcement learning, LLMs are great. These are the things which is they have their own side effects. For example, right, inverse reinforcement learning inherits human bias, and also constitutional AI has a lot of alignment tags involved in it because of the constraints involved in it. Tampering, like whatever the reward function comes into the result, it's tried to manipulate it by itself. So that's not actually good for to get a better intent for our humans. And also the cultural dependencies are there. What are the existing methodologies are doing here, right? Reinforcement learning from human feedback. So it takes like reward models learn these preferences and shapes agent policy via proximal optimization. Like constitutional AI also, it has a semantic gap, and these are all the methodologies are there, but they systematically fail under distribution shift. Like the autonomous systems are good in the training region. If you're going out of the training region, it's a out of distribution, then it may give a different result which is not in line with our human intent. And also there will be reward hacking. So it will try to perform very well. It is trying to give the reward, but the reward hacking happens there. So culturally it's not divergent. A lot of problems are there in an autonomous agent using all these methodologies. So we identified a gap, the several gaps we identified, and we come up with this DPA framework, which will resolve all these gaps about upcoming situations. Like you see at alignment tax, an agent is having a less alignment tax. Means what is alignment tax means? A performance degradation when injecting ethical constraints into the system, so that it will not perform very well. So the alignment tax is a problem, and reward hacking we already discussed, and then distribution shift. The agents are good in a supervised environment. It's an unsupervised environment. The agents may not perform well as expected by the human beings. So the main thing is that the regulatory and governance compliance. All the autonomous agents we have the regulatory compliance. So we have to really careful about the regulatory compliance and federated learning. So these are the gaps and these are the methodologies. So we have this framework called the dynamic pluralistic alignment framework, which has 5 steps in it, which has it will get the patient's data or input data as a weights and trajectories, and it will create candidate actions. And then next step, it will go to analyze the multi-objective state evaluation, like functional and ethical evaluation. It will be done. And then it will go to uncertainty aware. If there is any uncertainty in the state, it will do the penalizing, so that it will discount that uncertainty. And then next step, it will go to formal ethical verification. So like formal ethical verification is that there are safe sets configured over there, and if they are going beyond the safe set, then that will be disallowed. That state will be disallowed. Then you can go to the next one. So the finally is the formal constraint optimization. That is the main final action by the autonomous agent. So let's go with a real-time use case on this methodology. Take a case in an emergency room. We have an autonomous AA system. AA agent is there. So when you get the input data, say a person comes with a kind of a chest pain or a breathing problem, and without unclear ECG, and these problems came, and the agents will create a kind of a candidate actions like, okay, you can check up and go home. It's a discharge. There is no problem for the patient. And then you can, a agent can suggest that, okay, you have to go to more tests, you have to go to more tests. And then the third action you can create is that, okay, you can go to cardiologist to refer your stuffs. And the fourth one it can give is that, okay, you can go for invasive procedure. So these are the 4 candidate actions the agent can create. But we cannot take this all as it is, right? We wanted to go to the next step, saying that multi-object state evaluation. So with this, all 4 actions are evaluated against functionally as well as ethically. Functionally means how the test optimization, the treatment optimization, as well as ethical means how the patient is safety. All these aspects are evaluated in the multi-object set evaluation, and then it will go to the uncertainty aware reward penalization. So in this case, right, we have a lot of uncertainty here. There is a ECG is not clear, it's an uncertainty. And then ambiguity symptoms, it's an uncertainty. A patient can have a chance of heart attack. It's an uncertainty. So these are the uncertainty. In the situation of uncertainty, the autonomous agents without this framework, it will give an incorrect result or dangerous situation, dangerous results to the patient. So we wanted to disallow this uncertainty. So for that, it will go to a safe set. In the safe set, we will look out for the hospital procedure, operating procedure. And so when you want to go to invasive procedure, you have to do the pre-testing aspect of it. So in this case, right, all the 4 candidate actions, the discharge thing is disallowed, and then surgery, we cannot go because of uncertainty. And we have only 2 options available remaining is go for a multiple additional testing, and then go for a refer to cardiologist. So in the final constraint optimization, this framework safely giving a result, analysis and action to the patient saying that you have to go for cardiologist. So here we are bringing human in loop. That's what is an important thing. So this framework will help to address to the human in loop, go to cardiologist and get the safe result for the patient. These are the 3 methods, the objective, the formulas we have, multi-object utilization function, and then uncertainty aware penalization, and then formal constraint optimization. The results, we got these results from the stimulative experimental environment. It's not yet in production. So all these standard models improve the performance because they are suppressing reasoning capability. Whereas a DPA performs very well, even though the dynamically applying the constraints, not always we are applying it. And then alignment tax. Alignment tax, because you see the standard RLHF and constitutional AI have a lot more alignment tax because it is 100% every time they are using the constraints. But in DPA, we are not using the constraint, it's a dynamically applied, the constraints are dynamically applied based on this criticality and situation, where the situation, okay? And then there are as I mentioned, out of distribution, the other models perform very well, very less, and the DPA is performing very well, because we are giving the constraints on the situation where in a dynamic situation, adaptive way. So mitigation of, so what is the interpretation of the results here? So we are able to mitigate the alignment tax by adaptive context sensitive ethical weighting. And also uncertainty aware penalization helps to reduce the uncertainty for a result, for a very good result to the patient or the human intent, right? And then the next one is the deceptive alignment. So what is the summary finding here is that this DPA framework, right, can demonstrate autonomous agents be simultaneously high performing and robustly ethical. So with this, we get the harmlessness 94.2%, helpfulness 89.7%, alignment tax is reduced effectively 73% when compared to the other models. So in out of distribution situation, it is performing very well. So safety violation is less than 1% as well. So the next is extensions and limitations of this thing. So we have this, this is an architectural, conceptual architectural paper, and it has to go through all these feature works. It's a cross-cultural ontology to be done, and then since it is a real-time human in loop integration, we have to integrate with the hospital systems and high-risk domains, and also we have to develop multi-agent DPAs to support across the globe, and we have the standard element benchmarking as well. So these are the references which I go, and these are the ways you can calculate the helpfulness, harmlessness, and then alignment tax. Using all the weights, you can weight. So the DPA is performing very well on these areas. Thank you.
Sign off?
Yeah.
Okay. Thanks. So the next one will be 233.
Thank you. Next would be 233.
233. Mr. Vaibhav Mishra.
This is your presentation. All sitting here, kindly ensure your presentation has been uploaded on the Google Drive. The link is already been shared with all of you. Sir, are we on time this time?
Yes.
Are we maintaining the time?
I don't think so, but.
Request everybody to please wind up your thoughts in 10 minutes. And do not miss out signing the sheet which is right in front of session chairs. Check for the slides.
Light is visible.
Is it on full screen?
Yes.
Yeah, full screen. It's full screen.
And slides are moving.
Moving other. Full screen and moving.
Right. Over to you.
So today I am presenting a research paper on an AI-driven multi-source predictive maintenance framework, which I am integrating with sensor data, SAP S/4HANA EAM, and MES for adaptive maintenance scheduling. So the introduction and the background. So the Industry 4 demands a shift from rigid time-based maintenance to intelligent predictive strategies. And the traditional preventive maintenance causes a lot of over-maintenance and catastrophic failures. And the traditional maintenance strategy also results into overwork and wastage of manpower. Now to address it, earlier we brought up the IoT sensor data acquisition, which could capture the critical parameters of the machines, but it could provide only the current health of the machine. Now, to fill up this gap, unlike the traditional predictive maintenance system, which relies only on the time-based time series sensor data, we propose a model which is a hybrid intelligent layer that combines the structured and the unstructured maintenance data with real-time operational signals. So we are integrating the IoT sensor data, MES and ERP, SAP S/4HANA system, which contains the unstructured log, which has been filled up by the technicians in the field. So literature review, the sensor-based failure prediction. So the all important parameters such as vibration, temperature, pressure, current load can be pulled from the sensors and bring into the system. And using the machine learning and time series forecasting, we have the regression models, the neural networks for pattern recognition, calculating the remaining useful life of the machines. But here also there is a limitation that it cannot analyze the long text which has been entered by the maintenance staff. That's why we are doing an enterprise integration with the AI models in this paper. So the ERP technology, which is SAP S/4HANA, currently it is isolated, but we are integrating it with MES, the real time, which is providing the real time signals. And we are unifying it with the AI framework, which contains the sensor data. So this is the proposed framework, the system architecture. So it contains 4 layers here. So you can see that the layer 1 is here, layer 2, layer 3 and layer 4. From the layer 1, we are acquiring the sensor data. In the layer 2, which is MES system, we are storing the raw data of sensors and then processing it to the ERP software. ERP technology here is the SAP S/4HANA, which contains the asset information, the technical specifications of the machine, the historical breakdown and preventive maintenance logs, And we also have the AI model which is residing inside the SAP S4HANA system. And this particular AI model is analyzing the behavior of the machine, and it is analyzing the unstructured maintenance logs and coming up with the recommendations to change the frequency of maintenance of the machines. So if any machine is designed to do overhauling in every 24 months, then it can give a recommendation that, okay, let us do it in 18 months or increase the duration from 24 to 28 months. So it is a 4-layer architecture. Okay, now the data processing pipelines, the sensor data, which can have the minimum and maximum scaling, noise filtering, time series windowing, NLP tokenizer embedding, and the catalog codes. But this hybrid model of neural network, it will have the sensor data, ERP data, and it will join unified all this data into a single layer and come up with the predictive recommendations for the maintenance of the machines. So the function which has been given, the predictive function, is available here. There's MT equals to F, ST, TE, CH, and LH. So here ST is the sensor data, TE is the technical specifications of the machine, and then CH is the catalog codes, and LH is the natural language processing, which contains the long text and the maintenance logs filled by the technicians. So here, when we are integrating it with the SAP S4HANA system, at that time we are capturing the sensor data in the form of measuring points and documents. And on the basis of this, the AI model is sending the triggers, not only changing the maintenance frequency, but also the proactive maintenance, which are not the scheduled one. Okay, other than this, the adaptive PM cycle adjustment means that if there is an inspection which is scheduled in every 30 days, then it can say that, okay, let us do it in 42 days or 45 days. These kind of changes will not only save the manpower, but also reduce the maintenance cost. So this is the result and analysis sheet. So we have the KPIs. We have seen a significant improvement in the unplanned downtime. Unplanned downtime is reduced. Overall equipment effectiveness is increased. Yearly maintenance cost is reduced, and maintenance planner efforts are also reduced. And the final analysis in the form of percentage that which says that especially the maintenance cost, you can see here the yearly maintenance cost is reduced by 14.5%. So this cost related figures and accuracy has been achieved by integrating the ERP application SAP S4HANA with the AI data. So here the final conclusion, the primary innovation is the first closed loop AI system bridging IoT with SAP S4HANA via MES system. AI is actively modifying the maintenance plans beyond passive alerting. And validating the performance, we have the mean average error is reduced to 1.7 days. The false positive signals are now only 8%. And it is beating the LSTM and the rule-based AI models by 22.2 and 49.2%. And the operational impact, the downtime of the machines and the production line is reduced. The overall effectiveness of the equipment is increased by 19.3%. Cost is reduced, and planner efforts are also reduced. So for the future scope, we can integrate the procurement of spare parts also with this, means integrating the supply chain related part of the maintenance with this AI model, which can trigger the overall spare parts procurement on time, and it will reduce the unwanted inventory in the warehouse. And we can expand the natural language processing with a few shots industrial LLMs for orgs with limited log history, scale to multiple plants and additional asset classes. So this study was limited to only a few equipments for a period of 14 months, but we can scale it to a big manufacturing industry. These are the references. Thank you.
Thank you, Arun.
So the next one will be 234.
Two 34. This is your presentation, right? This is the one, right? Is the screen visible?
Yeah, full screen
Check.
and moving also.
Thank you.
Full screen and moving.
Sachin. I'll get next.
Hey, good morning. My name is Suchit Arela. Today I'll be presenting our research paper on graph neural network models for money laundering detection. So, in this presentation, I'll discuss the limitations of existing AML systems, why graph learning is important, and the proposed STAP GNN architecture here. So, and we'll also be talking about the experimental results and the future research directions of this. Okay, going on to the next slide. So, money laundering has become significantly more complex due to globalization, online banking, and cryptocurrency. And the traditional anti-money laundering systems are mostly rule-based, like they are flagged only when the transactions are of a fixed threshold, or abnormal transaction accounts, or suspicious geographic transfers. So as a result, the rule-based systems, they generate very high false positives and poor adaptability. So the opportunity here comes from understanding that the financial transactions are naturally interconnected, and money laundering is rarely a single isolated transaction. Instead, it involves multiple accounts, shell companies, intermediary banks, and layered transfers. And the related structure makes graph neural networks highly suitable because they can learn patterns directly from the network relationships. So this slide explains why graph modeling is critical for financial fraud detection. And in this, a transaction graph, what it mainly contains is nodes which represents the accounts, customers, or the organizations. And the edges, they represent the financial transactions between them. For the literature review, this slide, it summarizes the evolution of AML, the direction, the detection approaches, and yeah, that's it. So next, in this slide, we are going to talk about the contributions from prior work actually. So the researchers have proposed heterogeneous GNNs that model different entity types such as customers, accounts, banks, and organizations. So this better reflects real financial ecosystems. In this slide, we are going to talk about the research gaps. The first one is the scalability, and the second one is the temporal dynamics. So many existing models are static and fail to capture evolving laundering behaviors. And the other research gap is class imbalance and interpretability. So the interpretability, the financial institutions and regulators require explanations for why a transaction was flagged, and the other one is privacy constraints. The banks cannot freely share the sensitive customer data across the infrastructures. And in here, we are going to talk about the methodology. So the nodes, they represent the accounts, customers, and organizations as we discussed. And the edges are, they usually are the transactions enriched with the timestamps, frequency, the transaction amount, and risk indicators. Next comes message passing and embedding generation using GCN and GATs. So the performance is evaluated using the precision, recall, F1 score, and AUC ROC. And in here, we are going to talk about the actual STAP GNN architecture. So first, this is the temporal attention. So it is the time decay weighted message passing captures evolving transaction behaviors. And second is the neighborhood sampling. Instead of processing the entire graph, fixed size neighbor subset improve scalability. And third is the focal loss, where this cost sensitive learning approach gives higher importance to rare suspicious transactions. The next one is federated learning, which is mainly about the institutions collaboratively train the model without sharing the transaction data. And next up is the attention explainability. So this is like the giving the scores to the attention help identify which neighboring accounts influence suspicious predictions. And next up is the mathematical formulations. So the node initialization equation defines the initial embedding representation for each entity. And the temporal attention message passing equation combines the feature similarity, neighbor importance, and time decay factors. And finally, the attention explainability scores help identify influential neighbors contributing to suspicious predictions. And here is the end-to-end pipeline. So this it mainly summarizes the complete pipeline. The process starts with a raw transaction record collected from the financial systems. These records are converted into a dynamic heterogeneous graph. And next, the neighborhood sampling improves scalability for large transaction networks. And the temporal GNN processing performs time-aware message passing and embedding learning. So finally, the system outputs the ranked suspicious entities, risk scores, and the interpretable explanations. This slide talks about the results. So we compared the STAP GNN against the logistic regression, random forest, the support vector machine, and a baseline GCN model. Our proposed model has achieved precision of 0.91 and the recall of 0.88 and F1 score of 0.89. So this slide evaluates the computational efficiency and scalability. The traditional models like the logistic regression train quickly, but cannot model complex graph relationships effectively. The baseline GCN has achieved the strong accuracy, but they required highest training time and largest memory consumption. But compared to the baseline GCN, STAP GNN has achieved 27% more training time and 25% reduced memory usage. And for the discussion, the first temporal attention significantly improves detection performance because recent suspicious behavior is weighted more strongly than outdated interactions. And banks can collaboratively train models without sharing sensitive information here. For the conclusion, the research introduced STAP GNN and a unified neural network framework for money laundering detection. So the model simultaneously addresses the scalability, the temporal dynamics, class imbalance, interpretability, and privacy preservation. So for the future scope, they can process continuous evolving transaction streams using online learning. And secondly, we can also work on the cross model fusion, and after that we can also see some improvement scope at the adversarial robustness in this. So yeah, that's it from my side. Thank you everyone for your attention. And this work was built upon on the GNN's explainable AI and federated learning and financial fraud detections. And if anyone have any questions, thank you. Thank you.
Thank you so much. After the session, we'll have a group photograph so that you have memories of, so everybody be here. Next.
Next will be 226.
Should we take a break? Do you want a break, tea, coffee break, something?
Yeah.
What's your turn?
So did you sign up? Yeah. Oh.
What's your paper ID?
236.
236, Deepak. Yeah. And 3829, right?
393.
39.
Yeah, it is full screen. Moving also, full screen moving. Please unmute, you are muted. Yeah, I think it is unmuted.
Hello all, this is Deepak Kumar Giri. And I work as a executive director at Wells Fargo, and my job is around the electronic trading systems, and which is financial technology. And so this paper is written by me, the primary author, and Amit Mishra and Praveen Kumar Sharma, but I will be presenting it today. The title is Deep Reinforcement Learning for Adaptive Asset Allocation in Uncertain Markets. So the paper touches on the premise of how we use reinforcement learning in choosing the right assets meaning stocks, where you allocate the money. So although my experiment were with equities, the cash stocks, but this principles applies to any assets for that matter, be it crypto, be it futures, be it commodities. So I'll start my presentation. I know it's 10 minutes, so 11:31. Yep. The core challenges, right? What we have been seeing so far and why this paper makes sense. So the financial markets as such is non-stationary, but so far all the models which we were training on prior to AI were all stationary models, be it the Markowitz model or be it the modern portfolio theory, which is called MPT or the CAPM. Now, in this, I'm talking about deep reinforcement learning because it can capture that state very well. Although, uh, because there are multiple price points, it's not only the closing prices, but also the sentiment analysis, the news, the macroeconomics, the unemployment data, interest rates, all of that are factored in before stocks are either bought or sold. So again, coming back to the same, the market is not stationary, but so far we have been modeling it as a stationary. That is why the returns were not much. But here, deep reinforcement learning is able to get multiple price points. And that is how we would see how this gives a better result, and also the explainability part. Going ahead. So write this here. Right? Okay. Okay. Literature review. Okay. Yeah. Thanks. Okay. So here in this slide, I talk about how deep reinforcement learning has evolved over the period. How it started with a very basic one, and over the period we have seen greater improvement. And I'll finally talk about the paper or the idea which I'm presenting here, which is LSTM and deep reinforcement learning hybrid. LSTM stands for long short-term memory, and these were the historical models and how this thing has evolved. So I don't not want to touch more time on that. Moving ahead, the existing models, right? These were the gaps, and why this paper was written to address those gaps. Uh, there was not robust generalization. So far, we have been overfitting. So as long as the markets move in the same direction as happened historically, the models did great. But things like COVID, Black Swan moment, almost all the quant models crashed. Like if you look at 2020, whereas I've tested this on during 2020 COVID period also, and saw very good results, which I want to present it here. The risk integration. So we only look at the returns. How much returns are we able to get it? But we are not looking at the risks. Can there be one bad day which can take away all the profits we have made? Now, those models will not stand a chance. And how uh, the CVAR, which is value at risk, is also part of the model parameters. I'll be talking about poor interpretability. So far, all these AI models, what we see is a black box. We give a data, we see the output, but we do not know why it produced the output. And things like in the financial world, it is also important to know why did it either bought the stock or sold the stock. Why did it made that decision? Now, in this example, I'll talk about how I've added the explainability also as part of that. Uh, then coming back to the alternative data. Now, Twitter feed, social media, news, now all those were also input into the model. So on the real time, uh, the research what I've did is I'm also feeding in those data. So we are not only looking at the stock, but we are also looking at the real time market data and the sentiment analysis. If people are talking bad about NVIDIA, so we shouldn't be buying that at that time. We should be selling it because it'll definitely go down. So yeah, so that is also part of this. Simplified market assumptions. Normally, people do not talk about market assumptions. I mean, when you go and buy a stock and sell a stock, there's a transaction cost you need to pay to the exchange. Now, all the profit you make can get drained out if you do a lot of transactions. Usually, the models don't factor that in. So I've tried to factor that also. I've tried to factor the market impact, liquidity constraints, and slippage. Market impact is when you go and buy in a big chunk, you would end up moving the market up, which you don't want, just because which is going against you. So how do you break that into small chunks and buy it at different intervals so that people do not know on the other side somebody wants to buy a bigger amount? Uh, Liquidity constraint. Liquidity constraints is what if there is not enough stocks available, but your model says you want to buy 10,000, and there's the other guy not willing to pay 10,000. So you would jump up the price for that short term, and you'd be getting a bad price there. So you'd either break up into small pieces, look at different intervals, as soon as it gets available. So that also deep reinforcement learning does it very, very well. 3 minutes. This is this is the methodology. So far, I spoke about the problems and the challenges, and I'll quickly go over how this addresses it. Multi-source construction, hybrid LSTM attention, because long short-term memory. So the short-term and the long-term, both are given weights. Risk-aware optimization, interpretable output. So output should be interpretable. Why did we buy this or why did we sell this? So that we learn from it. This is the maths behind it. As I saw, talk about the risks. Now, the value at risk and how the alpha is our profit. But then we are more concerned on the risks aspect of it also. Just to not do overfitting. So we introduce randomization so that we don't overfit. Again, I compared with different various techniques, and this proposed DRL, which is this new technique, how it beats all of the previous models. So we got 14.1% return. This is tested on the US stock exchange traded stocks. And the Sharpe ratio was 1.58. So the Sharpe and the max drawdown was 11.8. So the Sharpe ratio is, it's not only the returns, but returns against the variance. So if you have too much variance, then that is not supposed to be a good model. Today you make a lot of money, tomorrow you lose. But your variance should be as smaller. That's when you have a higher Sharpe ratio. So this model, because we did that risk-aware optimization that contributed to higher Sharpe ratio. Max drawdown is the day in which you made the maximum money, the day in which you made the lowest money. That difference has to be lowest. If you look at amongst all, this is the lowest. So if you look at the graph, it's always at the worst, it is 11.8. This is a risk stability analysis. This is again talking about the results on the training data, on the test data, and how it is not overfitting as much. Well, there are others which did better than this in terms of overfitting, like MVO and EWP, equal weight portfolio. But overall, in terms of returns, this fares very well. Yeah, as I said, there is a return superiority. And there are two aspects which we look at: how much return we got and how much Sharpe ratio. In both, it does great. So I see, we as a team see that this is one of the models which could solve long awaited problems in terms of risk aware, getting data from multiple sources, and all of that. These are findings. This is the future scope. So far, we only did a research. What we did not do was real-time streaming integration, meaning real-time. We did not try to trade using that model. We did not get the real-time market news, real-time sentiments. We only did in the historical past data. Now that is something which we need to work on. The future XCI is the explainability part of it. We did, but we could do better on the explainability. Alternative data sources. I mean, there is no end to the data sources, right? There could be supply chain. Like if Tesla is doing well, who are the suppliers of Tesla? So it's not only the Tesla stocks will go, but everyone who is supplying to the Tesla stocks will go. So all this data is available in the market. Every company, you get to know who are the suppliers. If one of them is doing good, you know that the others will also do good. It's not now, but tomorrow. So you're getting it at a cheaper price today. So you buy it today before it goes higher. So yeah, so those are, and the global trade flows, all this data is available. There are data providers. Now we did not integrate those supply chains, but they could be added as well. There's a satellite imagery. So every company's satellite images are taken care. So if a company gets a lot number of trucks going in and out, it means that the company is doing great.
Even that could be a factor into your model. And you know that stocks will go higher because a lot of trucks are going in and out. I mean, people go to that extent just to look at predict the stock prices. Regulatory and live deployment. I mean, it's a very regulated market. We need to be compliant with the exchange, SEC rules. I mean, this was more on a research base. We did not look at all those compliances rules. When we go live using this model, we'll have to be compliant with those rules. Yeah, this is it. Yeah, thank you so much for the opportunity to talk. Yeah. Any questions? Happy to answer. Yeah.
Does these models also teach it? Will there be model teach it?
Yes, it will be. As long, the way it happens is if someone tries to trade using the same model outside, then that pie is shared between two of us. If there are 10 people, then that pie gets shared between 10 people. Then after 100 people, then it gets shared with 100. So then there is no value of trading with this model. So this is what happens with all trading models. It has to evolve. You need to find new way, new opportunity. Yep.
That's it. Thank you.
Thanks. Thank you so much. Thank you.
Probably take a break now.
Yeah. Thank you so much. There's a break for 5 minutes, then we'll restart. Like Sam. So we are back. Design. Set. Which one is yours?
388.
This one.
Yes.
Is the slide visible?
Yeah, the slide is visible.
Full screen?
Not yet. Yeah, now full screen and moving.
Wonderful.
One I'll do after, I mean, do you lunch break? But lunch break is after
Is one.
all the patients. So you're.
It's a tough session, Chair, isn't it? Lunch break is after all the presentations.
Then it's dinner.
True.
So
No, we'll break for lunch at 1.
What?
So before that, we'll
Yeah, I'll
quickly
cover one
finish.
now and then maybe after lunch.
Oh, over to you, Nitin.
Thank you. So yeah, I'll start. So my name is Nitin.
Oh, okay.
Yeah, once everybody is settled down. So hi everyone. My name is Nitin, and thanks for. Okay.
Which paper are you
So I'll be covering paper 388. So this is basically reinforcement learning with casual modeling for adaptive decision making in autonomous and intelligent systems. So I'll spend a lot of time on this one because I mean it clearly indicate that what exactly is current model and then why we basically need casual perspective and then what will be our proposed solution. So if you see on the left hand side in current RL framework that we have, there are three things that an agent do, right? What it action, rewards and state. And what we have done is that we have taken a lot of use cases, especially like robotics, autonomous vehicles, industrial automation, smart grid, healthcare. And there are like a lot of limitations that we have currently with this model that we think, I mean, we can overcome with this our proposal. Now, if you see, when I talk about limitations, we have relies on correlation, not calculation, requires large amount of interactive data, assumes stationary struggles in dynamic environment, sensitive to distribution shifts and unseen situations, black box policies with low interpretability. Now, when I say these limitations, so there are a lot of like we completely agree that when we uh, casual perspective, right? So there are a lot of things which I mean we thought of. Number one is dynamic and non-stationary environment, right? If you see environment dynamically and reward structure change over time, right? We predict a lot of things that based on data that we have, but sometimes things doesn't go as we plan or doesn't go as we based on the data that we have. Again, next thing is partial observability. So agent do not observe full state, right? I mean, there are a lot of critical variables that remains hidden, right? With this the current approach, we do have hidden co-founders. We observed that correlations may be driven by unobserved common causes, poor generalization. Now we basically know that policies learned in one context may fail in new or shifted environments as of now. We do have safety and reliability issues that we have seen with the current RL model. So based on these, I mean, limitations based on these pointers, our like proposed solution that we have is that in our casual aware RL architecture, we have five things which we are covering. One is environment, one is state observation, then we have casual model SCM, then we have action, intervention, and rewards. Right now, what are the key capabilities for like using this new RL architecture? So number one is your intervention analysis. So evaluate the effect of action by intervening on specific variables. Counter uh, Counterfactual reasoning.
So we basically consider alternative scenarios and their potential outcomes. I'll give you some example that why, like how we can use this one. Number third is casual aware policy learning. Number four is interpretability and transparency, which make like us to make a decision are explainable through casual reasoning. I'll give you an example. Like we are doing one very large scale transformation project where we are moving out from mainframe to GCP, right? And there are a lot of scenarios where I mean we are clear or we are taking decision based on the data that we have, but still we are seeing that the new platform is not behaving the way it should be, which should be much smarter, much scalable as compared to old system. But still we are seeing a lot of performance issues. Now why? Because we are not checking the complete picture, right? We are not covering holistically. So that's where like this is one example where we can use this architecture, which contains casual awareness. Now, in terms of research and gap needed, so I'll say existing RL method lack the ability to capture causal relationships, leading to poor adaptability, low interpretability, and unsafe exploration in dynamic environment. This is very critical need for a unified framework that combines reinforcement learning and with casual modeling to enable adaptive, reliable, and interpretable decision-making automation intelligence systems. Any questions on this one? Okay, I'll move to the next slide. So these are the key, studies contribution that we have done. We have referred, these research that were done recently, not recently, but in last few years in terms of using this casual approach. But we found a lot of limitations and research gap. Like the number one is like limited to banded setting. So that lacks integration with the full RL frameworks and real world autonomous system. So again, we see a lot of experience gap that the research that was done way back in 2015. Primarily theoretical overview. So it talks only about theoretical. We are not seeing any practical, scenarios that they have covered. They focus on explainability. They are explaining it very well, but still, we see a lot of gaps in terms of maybe comparing it with the real scenarios. Then we have limited applications to reinforcement learning and sequential decision making. We do have limited scalability and lack comprehensive framework for dynamic environments. And then we have given everything here. We can refer to it. Now, if I talk about methodology, this proposed research method employs a stimulus-based experimental framework to evaluate the integration of reinforcement learning with casual modeling in dynamic and uncertain environments. Again, like I said, so there are a lot of work that we are doing, and we basically are relying purely on data, what data is saying, but we are not capturing it holistically. So that's like one thing which we want to cover with this new method. A reinforcement learning agent interacts with scholastic environment characterized by both observer variables and hidden co-founders, reflecting real-world complexities. The learning process follows an interactive cycle where the agent observes states, select actions, and receive rewards. While SCM is constructed and refined using interaction data to capture causal and effect relationships among variables. This enables the agent to move beyond correlation based learning by incorporating causal reasoning into decision making. So this is where we are bringing this new, I'll not say new, but things which were not effectively researched earlier, right? So this actually is helping us a lot to make a right decision. Additionally, intervention analysis and counterfactual requiring additional environment and interaction. I'll go to the next slide. In terms of results that we have seen is that the experiment result demonstrate that the proposed casual reinforcement learning framework outperformed traditional RL method across multiple evaluation metrics in dynamic environment. The model achieves higher cumulative rewards and improved stability, indicating more effective policy learning under uncertainty. By incorporating casual reasoning, the framework reduces the impact of hidden co-founders and avoids spurious correlations, leading to more reliable decision making. The use of counterfactual analysis further enhances sample efficiency, allowing agent to learn optimal strategies with fewer interactions. Now here, like one key thing which I want to address is that based on this casual decision, we are trying to reduce number of interactions, and we are trying to use the interaction that we are having to make our decision much focused and better. Overall, the results validate the effectiveness of proposed approach in enhancing robustness, adaptability, and performance in complex autonomous systems. Discussion. So this basically the result that we got for so far is that this result said that integrating casual modeling with reinforcement learning significantly enhances decision-making performance in a dynamic and uncertain environment. By incorporating structural casual method, the proposed framework effectively captures underlying root cause and effect relationships, reducing the impact of spurious correlation and hidden co-founders. The use of intervention analysis and counterfactual reasoning allows the agent to evaluate effectively actions more efficiently, leading to improved policy learning and adaptability. Now here, one point which I want to add is that we also are focusing on security and reliability also while proposing this new model that we have. Compared to traditional RL approaches, the model shows more generalization, under distribution shift, and increased robustness to environment changes. Additionally, the framework provides greater interpretability, enabling clear insight into reasoning behind decision. Overall, the findings validate the effectiveness and casual reinforcement learning while highlighting areas for further optimization and real-world validation. Coming to conclusion, this research presents a very unified framework that integrates reinforcement learning with casual modeling to improve adaptive decision making in autonomous and intelligent system. By incorporating structural casual model, the approach enables agents to understand cause and effect relationship rather than relying solely on correlation. The inclusion of intervention analysis and counterfactual reasoning enhance the agent ability to evaluate actions more effectively and learn from limited interaction. Experimental results demonstrate improved robustness, generalization, and sample efficiency compared to traditional RL method. The framework also enhances interpretability, making decision processes more trustworthy. Overall, this work highlights the potential of casual reinforcement learning as a powerful paradigm for next generation intelligent system operating in dynamic and uncertain environments. Yeah, if I talk about future scope, future research we can focus on extending this proposed casual reinforcement learning framework to large-scale real-world applications such as autonomous vehicles, smart healthcare system, and intelligent wireless network. Incorporating advanced casual discovery techniques will enable automatic learning of casual structures from high-dimensional and dynamic data. So there are a lot of areas where we can use this method, especially in healthcare, especially in travel, insurance domain, banking domain, where we can take advantage of data plus casual model. The integration of deep learning with casual RL can further enhance scalability and performance in complex environment. Future work may also explore multi-agent casual reinforcement learning for collaborative and competitive decision-making scenarios. Improving computational efficiency and reducing model complexity will be essential for deployment in resource-constrained system. Additionally, incorporating human-in-loop approaches can enhance interpretability and trust in critical applications. Finally, validating the framework on real-world dataset and safety practical will strengthen its practical application and reliability. And these are the references that we have taken. Yes.
Do we have page on 321? Yeah. Oh, okay, sorry. And then
320.
Do you guys have any ideas? In a room, you have one paper.
So that I can see this
You
paper
can
box as well.
not with us.
Oh, yeah.
In the morning star versus you can just you like this.
So, scroll up. We need slideshow, right? Yeah. Let me do this. Because it's better you download it. That's really this. Oh yes, slideshow. If you do that, then present to view.
No.
And now you go to the one. We share. We share. This. But if you can open up in the notes, I think it will also show. Oh yeah, do not click. That's fine. Stop share. Just share that Chrome window. But we need to like start a presentation again. There you go. Hold on a second. Just stay because I guess I need. We need to like share this one, right? Yeah. I'll come here. I'll come here. Share. But still I will show up this. But it will not share it. You will see here it is screen mirroring, but actually in the conference it will not show. Yeah, but that's fine. Like I'll speak to it. That's like not an issue. Yeah. Do you mind like taking it more? Yeah, it's like yeah. So hello everyone. So I'm talking here today about how multi-agent systems are gonna improve business. Better? Yeah. So I'm Devtosh. I'm presenting my work on multi-agent AI system for adaptive business forecasting and optimization. In the current environment, the business forecasting has one of the biggest limitation is that it's not scalable. So that basically means is like traditional business forecasting models rely on previous data, which adhere to like previous past trends, which are not applicable in current decision framework for like bigger data companies that are driven by like bigger data sets. The traditional business models are not scalable. They are not AI driven, and they're like more like centralized system with a lot of like dependencies on like one single model or one single ML framework that kind of like drives the whole business forecasting, which is not really good in the sense of, because in the current day and age of world, like there's so much data that's being inputted through like getting funneled into like through like different sources. The business forecasting model needs to be in par with the data that it's receiving. So this is what my research focuses on. It focuses on the gap, and it focuses on like how can we achieve better business forecasting models with the help of like AI and multi-agent system. So diving a little bit more into the problem statement. So as I said, like the current the traditional business forecasting models are static, and they're not very flexible with the fluctuations of market. So what I mean by that is, like, for example, if you take into consideration a sales model like across like 500 like different stores, like if something were to change at this point of time, the forecasting model that predicted like what's going to happen today, tomorrow, or like probably a week into it, it's not gonna like hold to its standard. So what I mean by that is basically like if there's a like sudden change in
external factors, the business forecasting models is not able to adapt to it and change accordingly its predicted outcomes. It's all centralized. So what that means is if the model is a central model goes down, the whole business is now at risk of incorrect forecasting. And also it's not really good at handling heterogeneous data. So the research objective is to basically come up with a potential solution which utilizes multiple agent AI framework for business forecasting and also for resource optimization and making sure that the agents are capable enough to make decisions in real time. Here's a quick snap of the literature review of what's already exists out there. And as you can see, the majority of them focus on one part of that business case problem rather than a combination of that. So what I mean by that is for example, the first reference of Khatab here, you can see it focuses on business it's only focused on business forecasting, but it does not outline how you can probably get around it or a potential solution for it. There's other literature reviews on scalability challenge and how computational costs rise with agentic AI framework. But my paper, my research work focuses around how we can take bits and pieces from all of it and come up with a solution that is scalable, that incorporates heterogeneous data, and that also makes sure that it's making decisions in real time. So this is a proposed MAAI multiple agent AI framework architecture. So basically what it is it's multiple agents which are talking to each other, which are in their own environment, but they also have the capabilities of relaying their outputs and ability to interact with other agents in this whole model. So you start with the data acquisition layer, which is basically basically the agents mining the information, mining the data. There's a data pre-processing layer, which is basically you make sure that garbage in, garbage out. If you don't clean up the data, you're gonna get garbage results. So that's what data pre-processing layer is. It basically strips out of all the noise from the data. And then there's predictive learning layer, which is basically your agents running different ML models on the clean data from the pre-processing layer and making sure they're self-optimizing themselves every time they iterate over their learnings from the previous inputs. The reinforcement learning layer is the most important and crucial layer, which is basically that the agents are self-learning by themselves. They're making sure that they're keying in the important inputs from the previous layers and self-optimizing and making sure that they are adhering to the new standards as they set as the real data comes in and we are prone towards more fluctuating inputs. And the decision optimization layer follows the reinforcement layer, which is basically just making sure that the decision layer of the agents make sure they take in the data, they run it through a function, and they optimize and run from the learning output from the previous layer. So this is the basically the crux of the logic, if I would want to call it. So which is basically this is how the prediction function is working. Is basically it's a function of your input data and the parameters that the models or the agentic AI framework passes through it. So as you can see, the output is a function of both input and the model parameters. So which literally translates to the model constantly learning from itself and evolving as and when the new data comes in, so that it's not susceptible to real-time fluctuations, and it can handle that in real time and make decisions through reinforced learning and decision model framework. A quick view on the numbers here. So we looked at the linear regression, random forest, and artificial neural networks models. We evaluated metrics like mean square error, root mean square error, and MAPE, which is mean absolute percentage error. And so quick overview. The lower the number, it's better. So the proposed MAAI framework gives you the least amount of error across all the three error metrics that we are tracking, and it also yields higher accuracy percentage. which actually speaks to like how this model, this framework is better when you look at like your traditional forecasting models, such as your linear regression, random forest, and artificial neural networks. Getting more into like the adaptability performance model, which is basically evaluating how much time does it take for the model to learn or adapt to the new changes and fluctuations that are incoming through the data layer. Convergence, which is basically how soon the model converges the previous inputs with the new inputs, and learning efficiency, which is like reinforced learning, making sure the data, making sure the models are constantly evolving in terms of like learning and making decisions based on that reinforced learning. As we can see, the multi-agent reinforced learning, like the adaptation time is 9.3, which is like significantly less across all the other models. The learning efficiency is also high and like pretty comparable to like single agent RL. But the way the metric where the single agent reinforced learning fails is because of the adaptation time, 15.6 seconds on a single agent versus 9.3 seconds against multi-agent, which is a significant drop that needs to be considered, like when we're working in a fast-paced like business development forecasting models, and especially in like more volatile businesses like your asset allocations and like other like sales metrics that are like happening in real time, where the prices has to be like tweaked and like moved along in real time. So this is a small slide that focuses on how like the KPIs, which are like profit, cost reduction, and resource utilizations, are managed by the proposed MAI network. And as you can see that in the last row, the proposed MAI framework like outperforms all the other models in the framework that were tested. Getting on to the next slide. So basically, so the multi-agent AI system, although like it's beneficial, but it also has its own I would want to say like caveats, which is basically it requires computational overhead. But at the same time, it uses like agentic AI orchestration. So what that basically means for like for the deployment purposes is the way in which the agents are orchestrated, how we set up the whole system is very crucial, is so that we don't complicate and we actually focus on delivering good. Um, so basically, yeah, like to my findings here. ML MAI framework provides you like better accuracy. It provides more efficiency, and it outperforms like other models in the error metrics that we evaluated. It's a framework that works, but it also has to be deployed and used in a proper fashion so that where the agent framework and agent orchestration are properly chained, and we reiterate and we loop over the framework and the whole pipeline to make sure like the data is actually being used for efficiency and it's not working against itself. The future scope, which is basically on like how do we take this further? It's basically using like integration with IoT and like edge computing, quantum inspired optimization, which is like basically again we are already reducing the adaptation time with quantum inspired optimizations. Yeah, we're going to further reduce the time it takes for the model to like learn in a heterogeneous data environment. And industry specific adaptive forecasting system, which is kind of like unsaid, which is basically one model cannot fit for both supply chain, for healthcare, and for financial. So like you need to be cognizant of the fact that each model has like separate parameters that are driving the outputs for that specific industry. A short view on the references, and that's going to be my time. Thank you.
Yeah. All these stages with one large language model, foundation model that you're training on.
No, so a foundation model, because training our own would be, I mean, that would be a significant undertaking. Yeah. So
the slide shows all the agents. Yeah.
This one?
No. That.
Yeah.
The
current slide, is that we, can you make a figure of it? No, the forecasting or the optimization, either one of those.
Yeah.
Did you build a deterministic model for that, or did you let the LLM do the forecasting?
So a systematic prompt that basically chooses the model. So like it like uses like 3 or 4 different models and then evaluates the metrics and then chooses the best one for the incoming data from the previous layer. So it's basically like it's basically an agentic loop that works on itself, and like it has a threshold, and then like once it gets to a like certain value in terms of like the error metrics, it kind of like stops there and then it goes to the next layer.
So a fixed model to use.
Yes.
For forecasting and a model to use.
Yes. So each of them can have like multiple agents doing the work, because for example, like in the data collection, right? So like you have like data coming in from like different layers. So you would probably want like specific agents, like, and even like in any kind of like agentic AI system, you would probably have a parent model that can like drive the work and like distributes the work across like different like child models, and then it make sure like it passes through a judge gate, which is basically making sure the outputs from the base model are actually correct, because like AI, as we know, is prone to like giving stuff that's like not irrelevant. So yeah.
Consider using multiple agents, independent, as a council of experts or a model of experts to do each of those forecasting and optimization steps? Just a thought.
So can you repeat that question one more time?
So suppose you implemented this with what, ChatGPT or?
Yeah. Yes. Found.
So suppose you were to invoke Claude and Gemini and ChatGPT independently to do the forecasting and the optimization, and then bring it.
Yeah. So
yeah,
exactly. So what you're saying is basically is, rather than relying on one base model, like different models from like different vendors and see like what the outputs are. I see. I'm not. Yeah. But that's a good thought, because like personally, like even in the work that I do on the side, like I have noticed like Gemini 3 sometimes like outperforms like Opus 4.6 in like critical thinking. It takes a little longer, but it does perform like really good. So I mean that's a good thought, like that could probably like benefit from that. Yeah, sure, no problem. Good questions.
You can do it. Yeah, so let's see. So
Next is 375, right?
it's you do that.
Surya.
Yes, ma'am.
Yeah. We have this.
So it's okay. So next paper. Quick check if the paper is visible. Yes, ma'am.
Yeah, but the paper is visible full screen as well.
And I'm changing the slides also.
Yeah, moving as well.
Wonderful. Over to you, Surya. All the best. Come. Thank you so much.
Hey everyone, good afternoon. I'm Surya Penticota. I lead the enterprise talk, and really excited to be here and presenting this paper in front of you. So today we are going to talk about one of the key challenges that industry is facing today, especially with network security and interpretation of network logs and getting the right telemetry of it right. We're working at a place, at a world where the traffic telemetry and metadata is really crucial to be successful in defending against sophisticated threats. As many of you may have known, the recently There's a lot of new models out there in the market, with whether it could be Mythos or whether it could be OpenAI's latest model and whatnot, have really smart ways of not just defending but attacking, right? They're able to generate sophisticated network layer attacks and get to the base of the system. So this paper is essentially an answer to today's challenges with critical limitation in network security that we see. The biggest gap that we observed in today's world when it comes to quantifying the threats and adding defense mechanisms around threats and whatnot. The gap is essentially around the federated learning and expandable AI areas. And the motivation is to build defensive mechanisms across IoT, Wi-Fi, wireless networks, and whatnot, right? So that's the whole background of this context around this, and the motivation, of course. In the research, there are definitely multiple areas where there can be improvements done, especially on lack of unified frameworks, insufficient expandability in FL and NLP, absence of comprehensive evaluations, and so on and so forth. So let's dive a dip into the studies included in this research. Obviously, there's a lot of research done with RAG and industry standard research to get to the bottom of it and help derive the research towards the right outcomes. And so this is a very important area that I want to dive into. There are around 10 steps or 10 stages, I would call, in this methodology. One, data collection, right? So in any given enterprise, data is the goal, right? Data is definitely the goal, and data is where the heart and brain works on. Like data is essentially like blood to the human body. Data is for any enterprise, right? So when you look into data, in order for us to get heterogeneous data sources, diverse data sources, we dive into network logs, system logs, threat intelligence feeds, vulnerabilities, user access logs, and whatnot. So these are important areas where we can drive, where we can learn, where we can infer, where we can train our models to take enhanced measures in protecting against threats out there in the industry. Once we have the data, which is blood, we need the body to function, and that's essentially where the construction comes in. In order to construction the graph in graph neural networks, we have these telemetry, or we have these data sources and whatnot. We build a graph around it, we build edges and inference models around it, and we build paths around it and whatnot. That's the second important model. That's when GNN comes into picture, graph neural networks. GNN would help us to convert this data into structured formats and learning nodes embedded into the patterns of network, patterns of traffic, and patterns of analysis. So far, the industry aware of GNN, and they have built structures around GNN, but the missing part, the secret sauce, is causal interface. So obviously, as we know, GNN might not solve all the world problems, and that's when we get into causal. In causal, there are 4 key parameters. Obviously, structured learning, which discovers, or which the patterns that we get from GNN and convert into a good learning model. And obviously, there is parameter learning, which estimates the causal capabilities, right? It also estimates how causal is performing and whatnot, doing like a validation of our causal layer. And then we do calculus. Calculus is essentially where we do a lot of math, a lot of permutation, combinations, and all those concepts come into play to ensure that we have the right data structure and we have the right causal interferences going forward. Last but very important is what if analysis. It's also called as a counterfactual reasoning, right? Because we don't want to have any prompt injection, we don't have to have any AI model leakage and data leakage and whatnot. So that's where this integration factor plays a very, very important role for our encoding. And then comes to our 5th stage, which is prediction and risk assessment. So in corporate environments, risks are one of the key main factors, and risks come with their own price, right? So if there are risks associated, there are vulnerabilities. If there are vulnerabilities, there is a risk of major attacks. And if there are attacks, then there's definitely a financial cost involved. Price. So obviously predicting those risks and converting them into financial loss and whatnot are kind of very important prediction gathering areas for us. So that's where we have attack, intrusion prevention, prediction, which then goes to prevention, propagation analysis, and risk scoring. So each of these attacks comes with their own baggage, and these baggages will be in different colors, right? Few baggages could be the nature of the attack, few baggages could be the vulnerabilities associated with the attack, few baggages could be maybe hackers somewhere asking for ransomware. Cryptocurrency will also be one of those baggages. So getting the data of those packages, especially from threat intelligence feeds, and adding it to the model to take sophisticated decisions is what very important for us. And that's what prediction and risk assessment step does. Once it is done, that's when we go to the explainability and interpretation. Here is where we have GNN once again coming into play to do attention mechanisms, and then it also does like causal explanations, and lastly we get an output. So output will also be in different formats, right? One is the root cause identification. Every attack comes with a root cause, and that root cause is where is one of our output after this interpretation. And then we have like critical components as well, like we call it as crown jewels in industry terminology. So crown jewels are where critical data is stored in industries where we have Amazon an example, right? And Amazon lives and breathes on e-commerce, and e-commerce can only survive with financial data, and financial data is stored in PCI zone, regulated zone, DMZ zone. So that's essentially where the crown jewel is. So we don't want these attackers to go take control of these crown jewels and then cause damage to both reputation as well as financial losses, right? So that's why the crown jewel component is really important. And lastly, human readable justifications. Of course, we are using NLPs, and output is something that we would need, which is human readable, right? Especially building reports to executives, building reports to leadership. It's really important for us to speak and drive things forward. It's like almost similar to a cinema, for instance, right? We have to go touch audience, and that's essentially where output is really important, to speak the same language of our audiences. So that's where human readable justifications come into play. Once we are done with this step, that's when we go to seventh step, which is intervention and mitigation recommendations. Obviously, we do all the analysis, we get all the metrics, we get all the data, we get all the signals, I would say, from this GNN processes, along with our casual interference model. That's when we go to mitigation recommendations, because every attack comes with a few steps, right? Like every attack comes with their own mitigation strategies. So doing thorough analysis of what mitigation works best in case of an attack is where we come in, and we provide the whole optimal on mitigation, and also work on mitigation strategies. These mitigation strategies are interlinked with our step 6, where we build executive level reports, also get leadership buy-in to take policy access controls and whatnot. So once the mitigation is done, that's when we come to the next stages, which is learning from the data. Model training is really important, right? There's a supervised and semi-supervised model learning, because we have to continuously train the model with the latest and the greatest threats. Obviously, for this particular paper, to build our own model as well with the data, not just relying on industry foundation models. We've also used sophisticated models across the globe, not just in the US market, but we also gone to a few models in China and learn from it for sure, and build our own model and whatnot, and ensured that this is bulletproof approach in driving the best out of chaos situations to do the best out of it. Lastly, coming to evaluation, again, is really crucial to ensure that we don't have any false positives, we don't have any signal noises, we don't have any data leakage and whatnot. That's essentially where we have did thorough evaluation, and obviously there are a few steps that were encountered during the evaluation phase that helped us to mature the model, that helps us to mature the data sets and whatnot. Structured hamming is, SHD is one area that we have invested in. Robustness to adversarial attacks, rule-based, signal-based ideas, intrusion detection is one area where we were able to use it to not just detect, but also mature the detection models and engines. And it's a continuous enhancement process, right? And evaluation is really crucial for us to understand the gaps in the model and the gaps and mature in the upcoming steps. Lastly, out of all this, very important area is development and continuous learning. So once this paper get published, obviously we also got interest from our cross-functional partners, interest from a lot of industry native cybersecurity firms actually who'd want to invest in this and try to get the best out of the model and incorporate into their detection response processes. That's where one other area where we got a good support on the framework as well. So that's mostly around it. And again, there's a possibility of continuously auto scaling, enhancement, growth, and whatnot, right? So these are the results. This is one area which we played a major interest as well, because obviously ultimately we'd want to see some results and enhance and bring something new to the industry standards, right? So on the left pattern you'd see the proposed model achieved around an AUC of 0.8787, which is significantly higher than the current standard, which is around 0.70, and GAT of 0.76. Robustness is one other area where we were able to use this framework to demonstrate high resiliency against adversarial attacks in real world deployments as well. So that's essentially where we have been using this model and training our industry standard AI models. The F1 score as well improved for sure, especially around structural hamming distance, SHD, compared to rule-based ideas and other priorities. So these are the results, and more than happy to share details around these results. And obviously, our goal is to get some competition around and continuously improve the results and whatnot. Again, obviously, this is these are a bit high-level details about the model and how it works in the formula and whatnot. Yeah, I mean, obviously, I want to conclude by saying that this research presented an integrated framework in combining both GNN and causal interference to enhance the cybersecurity complex networks. We established work around promising direction for intelligent, explainable, and proactive cyber mitigation systems, because if you all look into the industry, cyber threats are number one damage causers and breaking points for industries, and we would want to tackle it, the challenge. Obviously, future research can expand to 5G, 6G networks, massive IoT ecosystems, and electric vehicles as well. That's one area which we are definitely looking into expand this, not just the enterprise world, but also electric ecosystem, grid ecosystem, and whatnot. And also, we'd want to incorporate this with federated privacy learning and privacy principles and proactive threat mitigation rather than just detection principles. Yeah, these are the key references, and yeah, if there are any questions, I'm here to take questions. Thank you.
Slide show your slide. The one that showed your process. Yeah. Okay. So on the green, the data coming in, it's going to be panel, right?
So that's a good point, actually. I mean, we try to get real data, and we try to we did a bit of fake. I wouldn't say fake with the right word, but we did get real data, and then we desensitized it. Exactly. Yeah. Yeah. It's
Python library.
Oh yeah, of course. Yeah. So tabular form, CSV format in theory, and then
so it's a table.
Yeah, and then we convert it into a graph through Python process. Yep. Correct.
And then from the Python to create the GNN. Sorry. So from the graph, create the encoding into a GNN. Use another.
Yeah, we used another. We used Go here. To be fair, Go language. So Golang is what we have used because, definitely. Yeah. Sorry, I didn't go deep into the languages and processes, whatnot, but yeah. So Python is done, but we used Go because in order for us to convert this into encoding processes, Go is like pretty fast, pretty quick. Because again, from this layer to this layer, it's really important for us to be quick, right? And that's when encoding is really crucial, and that's where we use Go. And from once the Go is done, again we came back into causal interface as well. That's one loop, and causal is also coded in Python, and we incorporate it into the platform.
And you use an open source model to encode the GNN?
Yes, yes. Encoding techniques are open source, of course.
Goes into an open source
Yeah.
matrix and gets the weights.
Yes. Correct.
And then that model then can be interpolated or queried to get your causal the causality.
Yes. So yes, correct. So once we have this doing our encoding, and then that's where we used causal interferences to get the right structured learning and whatnot. Thank you. Thanks, everyone.
Like this. Next is 397. Thank you. You're back.
Yes.
Yes, sir. Nitinji, right? This one, 97.
Everything's good. I think needs actually.
We can see the slides,
Wonderful. Thank you.
full screen moving.
Perfect. Thank you so much for continuing. Over to you.
Hi again. My name is Nitin, and I'll be covering this paper as well. So this paper talks about modeling interdependent drivers of robust AI deployment and analysis using MCDM integrated framework. Again, my name is Nitin, and I'm working for Coforge as an architect. And I'll go to next slide. So this is the like kind of introduction that what is background, what is motivation, and what like gaps we have seen so far. So in terms of background, you know that rapid AI adoption across sector face challenges in robustness, transparency, ethics, and governance. Now this is one of the key area where like we are seeing that adoption is one of the biggest challenge when we talk about AI. A lot of people have different perception that how AI will behave or how they will safeguard their job, right? So that's where like we want to make sure that they understand AI is not to take jobs. AI is to help them. To speed up their work that they're doing and to bring more quality in terms of the work that is getting done. In terms of motivation, we want to make sure that we are developing systematic understanding of interdependent drivers for responsible, trustworthy, and AI deployment. So, in terms of deployment, we want to make sure that we have some factors in terms of motivation. Last thing is risk gaps that we have. So, we have seen like lack of integrated MCDM modeling for causal dependencies. I'll move to next slide. So, in terms of literature review, these are the key studies that we are focused on. These are the key factors you can say. Number one is trust. Number second is explainability. Number third is our data governance model. Number fourth is our regulatory compliance and organizational readiness. That is that organization is ready, or should we do some kind of prerequisite work that has to be done before we even implement. In terms of gaps, like we have focused on individual factor focus, insufficient holistic view, lack of hierarchical. One second, sorry. And then need of integrated MCDM approach, DMetal plus ISM plus TOPSIS. Right. In terms of methodology, our focus was like on number one is on research design, which contains mixed method, thematic analysis plus DMATL plus ISM plus TOPSIS. So these are four components that we have covered as a part of design. In terms of data, we focus on literature plus expert pairwise comparison. We have 10 different advisor like drivers which we have identified, and we'll talk more about that in our upcoming slides. In terms of technique, our technique was based on thematic coding, causal metrics, hierarchical structuring, and ranking. Now, these are the results and analysis that we have seen so far by implementing this model. I mean, if you see like we are getting like for factor, these are the results for transparency. These are different 10 different factors which we have taken, and you see these are the groups that we have taken so far. Again, these are the further results and analysis in terms of relation and prominence that we have taken. Like we have taken trust, transparency, data governance, ethical alignment, transparency, model robustness, regulatory compliance, and risk management. These are like further results that we have seen in terms of ISM, multi-level hierarchy, foundational dependent outcomes. You can see that at different levels, uh, what exactly we are capturing out of those 10. So like on layer 1 or level 1, you can say we are covering D1, D2, D3 compliance. On level 2, we are covering data governance. Level 3, sorry, we are covering tech infrastructure, user compatibility. On level 3 again, we are covering model robustness, we are covering compliance, and then on level 5, which is the highest, is user capability. And on the left side, you can see that the values that we are getting as a part of these metrics. Further, if we want to divide them into 10 different, models. So these are the like based on rank. Trust is number one. Then we have model robustness. Then we have regulatory compliance. You can see all the values: transparency, risk management, ethical alignment, data governance, technological infrastructure, organizational readiness, user capability. In terms of discussion, we have covered three different factors. One is our trust and robustness and foundational, improved cascade to organization outcomes. We have covered like converges with prior work on ethics governance, but adds structural causal prioritization, highlights need for systematic non-siloed AI deployment strategies. So we have like taken few example of like how we can do AI deployment. But before we do that, we want to make sure that we are covering all 10 metrics that we have. Conclusion. So overall, like we'll say that this MCDM framework shows a trust, robustness, and compliance as dominant casual driver. Implications, I'll still say that we still have like few implications like guide policymakers and practitioners towards responsible AI implementation. So AI is not that simple that we can implement. We have to do a lot of prerequisite work before we do anything. And we want to make sure that we have right standards in place, we have right policies in place, we are covering security, we are covering compliance, everything before we even think of putting AI in picture. Because AI is good to have, or AI can help us, but parallelly we have to make sure that we are keeping security in picture. In terms of future scope, we can use some extension for MCDM that actually will help us to scale this up. Limitations, like again, we don't still have lack of expert judgment, sensitive subjectivity, static known dynamic modeling that we have. These are the key references that we have taken for this research paper. Any questions? Thanks.
Yes.
paper number is?
245. Yes.
Is your paper, right?
Yeah.
Yeah, full screen. Yeah, moving as well. Full screen and moving.
Wonderful. Thank you so much. Over to you, Sumant.
Hi everyone, this is Sumit Banerjee. I'm a senior software engineer in New York City. Uh, and just everyone can listen me, hear me. Okay. So my topic is AI-based optimization of nanostructured material for solar energy harvesting. So the background of the problem of my topic is the increasing global demand for clean and sustainable energy has accelerated. The research in the advanced solar energy harvesting technologies and conventional photovoltaic materials often suffer from limited energy. So the motivation of this topic is like AI-driven approaches can rapidly predict material behavior, optimize multiple parameters simultaneously, and reduce development time. Growing energy demand and environmental concern require efficient renewable energy technologies. And the research gap is like existing optimization method often focus on a singular performance metrics rather than balancing efficiency and stability. And the traditional experimental approaches require extensive laboratories testing computational resources and limited rapid material discovery. So we identify few gaps, like the research gaps. Those are like limited integration of AI model with real-time experimentation validation, experimental validation. Existing machine learning model often lack interpretability and transparency. Limited research on hybrid optimization approaches combining GAPSEO reinforce learning. The methodology is like we divided in three parts: like research design, data collector, tools and technique. Like in research design, we did machine learning based predictive modeling, multi objective optimization techniques, computational material simulations, staticals perform evaluations. And in the data collection, we did publicly available research data set, published scientific literature, computational simulation outputs, and we use tools and techniques. We use supervised machine learning models, predictive models, algorithms, and deep learning frameworks. These are the few result analysis and key findings. Like AI optimized nanostructure material achieved 25% energy conversion efficiency compared to 80% of conventional materials. The AI model achieved 92% prediction accuracy and 90% of converse rate. AI-based optimization demonstrated like superior computational efficiency and a strong generalization under like various environment conditions. So the discussion is like interpretation of the results. The results clearly indicate that AI-based optimization significantly improve the performance and of nanostructure material used for solar energy harvesting systems. Like comparison to the prior studies, earlier studies mainly focused on either material development or optimization techniques separately. The present research integrates AI, machine learning, evolutionary optimization to unified framework. Compared to prior approaches, the proposed method demonstrate better efficiency, reliability, scalability, and cost effectiveness. These are the few summary of findings, like energy conversion efficiency improved from 18 to 25%, cost efficiency improved from 60 to 85%, material stability increased like 72 to 90%, and implication like AI-driven optimization can revolutionize the design of the next general solar cells. Integration of machine learning with nanotechnology enable intelligent material discovery and adaptive optimization. The future scope is like extensive of study, integration of real-time experimentation, validation of AI optimization models, development of explainable techniques for improved interpretability of material predictions. But there are some limitations, like the study preliminary realize simulated and secondary data set rather than extensive real world. The limited of high quality of labeled data sets may affect the model generalization. Also, the AI models may suffer from interpretability and transparency issues. And these are like few references. Yeah. Thank you, everyone. Thank you.
Thank you.
I'll present both the pages together. Or I also send my details to you.
Yes, I'll take it. What's your paper ID?
247 and 248.
247, right? We wanted you to be there yesterday also, but somehow you couldn't connect.
Oh, you could have told me because
I have number. We'll discuss after this presentation.
Because you are a professor, I'd like to be in touch with you because I'm doing a lot of this thing.
Absolutely. So it should be long lasting.
Yes, it's
After this presentation, we'll sit and we'll discuss it.
perfect. Thank you.
There you go.
Yeah, full screen and moving.
Quick check. They're in India. It's
very late.
late evening, so I don't ask them. I'm just checking with. Thank you so much. This is Dr. Pranay.
Oh, okay. Dr. Pranay has been like wonderful.
Over to you.
Thank you. So very good afternoon, everybody. Hello, session chairs. I will be presenting on the chaotic metaheuristic driven big data intelligence, and my paper ID is 247, and my affiliation is University of Cincinnati, but I work with JP Morgan Chase. So just to give you a quick introduction about the background of the problem, the era of big data brings challenges, in terms of volume, velocity, and the variety. So the motivation behind this was to introduce the chaos theory, which can enhance exploration versus the exploitation balance and optimization. And the research gap that I'm trying to solve here is the traditional gradient based methods that we had been suffering from the convergence latency, and now we need a intelligent and scalable optimization frameworks for deep learning in big data and environments. So on the next slide, I'll just walk you through the literature review where we will be looking at the key studies. The key studies are, we are looking at the distributed frameworks like the Hadoop, Spark, enabled concurrent processing, CNNs, RNNs, and on the research gaps that we have identified so far are the gradient descent methods, which have slow convergence and local minima issues. And hence there is a big need of chaotic integration to improve such diversity and avoid the stagnation. The methodology I followed was the research design, which is the quantitative experimental research. The data collection was mainly on the high dimensional feature space from IoT devices, sensors, and the digital platforms. The tools and techniques are the logistic chaotic map and the hyperparameter optimization for learning rate using the batch size and the network depth. And these are the results and key analysis. So the accuracy that we found in the traditional DL was 82%, and the new chaotic metaheuristic was 91%. So we saw improvement of 11%. Same goes with precision. It had 80, and now we see 89. So we get around improvement of 11.3%. The recall has also improved by 12.8%, and the FN score has also improved by 12.7%. And on the discussion side, the interpretation of results are basically the chaotic is giving you 11 to 13% of gains and the 93% conversion rates, which we were not able to achieve in the gradient descent methods. And the conclusion is that since we achieved a 91% of accuracy and a 30% energy reduction, we have improved exploration and exploitation balance via the logistic chaotic map. And yes, and the implications are that it enables efficient processing of massive and high dimensional data sets. The future scope that our team has been thriving for is basically integrating this with the edge computing for big data environments and the application of other chaotic maps like the trend sign for performance and comparison. And right now, definitely we have some limitations on the computational overhead because of the chaotic sequence generation. And these are all the references that we took for this paper. Thank you so much. Probably I'll start with the next paper also, if you're okay. How do I find it? I was able to. I think better if you do it.
It's absolutely fine. This is the one, right?
Yes, 248.
That's it.
Sumit?
Oh, it was disconnected. This one side.
Yeah.
It's not full screen.
Yeah. Happy? Is it full screen now?
Yeah, it is.
Tough people, no?
Yes.
Like our session 10. Yes, over to you.
Thank you so much, ma'am. Hey, folks. Hi again. My name is Sagar, and I'll be presenting on the multimodal deep learning framework for our context, our AI and VR systems. The paper ID that I'm presenting is 248. So the background of this data problem is basically we have a lot of AR VR systems that need smart context our capabilities for the personalized interactive experiences, and single modality systems like the visual only lack comprehensive understanding, and hence the motivation of multimodal data using the visual, audio, spatial and geospatial can enable intelligent decisions. Deep learning can model complex relationships across the modalities. Uh, on the literature review side, we have key studies like the multimodal fusion that combines gaze, gesture, and speech for natural interaction. And on the research gaps, we have like insufficiently labeled data sets for multimodal AR and VR. So the methodology that I followed was basically the systematic experimentation, development, and the quantitative validations. The data collection was mostly done by the visual, audio, spatial, and the geospatial from the AR and VR environments. And these are the tools and techniques that I used. One was for early fusion, one was for the late fusion, and the last one was for the attention-based fusion. When we go to the results and analysis, we see that the CNN, RRN, and the multimodal and the attention based all have accuracy of 75 plus. And by comparing all of them together, I see that the attention base gets the maximum number of accuracy, and it definitely consumes a lot of memory, but at the same time, it gives you the accuracy and a high precision and recall scores. So definitely, as we see, the multimodal models outperform the uni model by 10 to 14% across all four metrics, which was the accuracy, precision scales. And when we compare this with our prior studies, the attention mechanism provide superior cross-modal relationship capture versus the early or late fusion. So the hybrid fusion is basically what we should be thriving for. And the summary of this findings is that we have achieved 92% of accuracy with 40 milliseconds of latency suitable for real-time interaction. And we have effectively integrated the visual, audio, and spatial inputs into one model. The implications, the implications are basically transforms human computer interactions through natural multimodal understanding. And the future scope that we basically look for is deployment on edge services or edge devices using model pruning or quantization, and integrating this with the reinforcement learning for user specific personalization. And definitely we are also going to look for self supervised learning to reduce the dependency on the labeled data sets. And yeah, these are all the references that we took for this paper. Thank you so much. I'll just open up the forum if you guys have any other questions. Thank you, everyone. Thank you.
Did the people for afternoon come here?
Yes.
Oh, you
So we are breaking for 10 minutes for lunch, and after 10 minutes, we'll be back for rest of the presentations. After that, you want to give first? We can do it after lunch, right? Enjoy your pizza.
Because it doesn't always come from there. They're not like the best. I will tell you more. Okay.
Thank you so much. Yes. Yes, we got mentioned. We wanted to do it last time also, but yes, and it was under construction, remember? And we have a way right at the back. Okay. So you can see again from the naked eyes. Yeah. And next year, event will be better because this syllabus, maybe a month back, we decided that we will be doing it better. Otherwise, we plan to. Oh, that's right. Oh, that's it. Okay. So we somehow managed to reach it. Okay. Okay. Oh, it's shared school. Okay. So it is the okay. So when the children don't mention, I separate property. Yesterday, yes. Yes, I still have my, give that here, it's like, don't you have that one, that's how it is. This one again, it yesterday, okay, it is very nice. David, the soldiers, okay. Well, that's yours. Yes, that's it, yes. And, okay. This is Central, right? Yes, that's it. Yes. Yes, I told you this also, that I'm waiting for Rana because she told me she'll be here for both the days. So how is this? Because both the days. Yeah, they, you have to be late yesterday, but I didn't know. I was an hour away. I wouldn't have gotten it 30 or 30. But you're so happy to manage it. Yes. Definitely, it's otherwise it's a fight because it is only the presentations. And for all the officials, they've left yesterday. That's still good. When did you go back? I'm back on 17. Okay. So I'm here to go back. And then I need to go back to FGO. Okay. So 15 has been FGO. Yes. 16 has been 17 has flight back Monday. Okay. 17 is yes. Yes, we have been all over. Okay. So where do you stay here on Long Island? Yes, I'm just staying in San yeah, plus it's oh, yes, staying in San yes. Right. That's what it's it's very full of life. Okay. There we go. Like small here. Oh, they're chilly, yeah. It's just a damp outside, yeah, I don't think the heat's on anymore, right?
Thank you so much.
Thanks for coming and
Yeah.
absolutely.
Let's keep in touch.
Of course.
Looking forward. So Ajam, you are in the city today?
I will.
Okay.
I told you there's alumni before, so I'm doing it, everybody must finish.
Oh, nice. I'm also doing another conference.
Where?
New Jersey में लगा हूँ, लेकिन conference in New York में. New Jersey में Edison. अच्छा अच्छा रिपीट
All the other things I have, that's what. That's what it's famous for. Seguro que habrá 20.000 años, pero yo no diré que se lo da por el por ahí salió la
Last year we have यहाँ पे लेकिन
Last year we welcomed her as chair of IIT Law. And as a nation, we discussed that she's You're welcome. Understand what is this?
It's the close up here. No, that's not okay. She's a
No, no. I just want.
Next year we can do it as you.
I put all the photographs on the side also.
Okay. Yeah. And all of us can.
The poster, there is a poster of it.
The same poster I have. Let me put it. Yes, yes, I have. Just give me a second.
Perfect, such a clear.
We'll have one group photograph here also. Can you come with us? She will also be with us. Check, check. Check.
One second. You can take after them.
मुगल सल्तनत बहादुर शाह जफर के समय
Thank you, sir.
Should I change the screen now?
Oh, it's okay. I see. Last 1 minute.
No, no problem.
Yeah.
Why don't you start? He's very joyful. Since morning, he has not spoken other than the presentation.
I was making rules.
Other than the presentation.
No.
We'll have a group photo. Yeah, after this, you can have 2 pictures. Okay.
But then if I make it more brighter, it's I put it in the meters. It's just you. Oh, sorry. I put in the university. That's what you say. Yeah. I think probably my speaking. Oh. And then it's I'm not back up. Just a moment. Thanks for the growth. We are going to do a group photo here. Okay. Oh.
We already had one outside. Let's do it. Rana is also here.
Yeah, definitely.
Everybody, we are so happy we have Rana running green with us. She was, last year she was the ICP chair. And we are so happy because she was one who was very instrumental in going for ICP honors. So thank you so much, Rana. Thank you so much for coming here. Are we done? Everybody? Can we have this in the background?
Yes. Do they have any, what did I say? Bags or anything? Yes. Bags or
No.
Oh, I was being told to store the Poga, so I was like, maybe I can keep it. Yeah. Click this one.
Oh, the full screen, okay.
Yeah.
Isn't this good? Let's have a photograph here.
Zoom.
Okay. Oh, yes. Perfect. Perfect.
Yeah.
Like a mic for the phone for the picture so that I can this mic. Thank you so much. You're looking good. Don't look at the mirror. Okay. Why is that? On the back.
Where would you like focus?
The form. It's not about it. Yeah. I'll come to the back. And go to the back. You want to with you also, right?
Yes, obviously.
He's the one who's on you. Other than his presentation.
Great.
Thank you so much.
Yes.
I also present. You are the okay, present.
Yes, yes.
Send the details, okay?
Yes.
Yeah, bye-bye.
Bye-bye. We are back to our presentation. Right? Who's next? Oh, you were left to give, right?
You guys are free. And you guys take over the session and enhance no, it's only the order. So we can just find a way to
This is right?
Yeah.
One you presented.
Yeah.
Everyone says that sound. I think so. It's only that. I don't know.
This is your plan. This one.
This one, yeah.
Oh, you're from Pace University?
Yeah.
Yesterday your president was here.
Oh, yeah, this
Pablo?
Pablo, yes, yes.
He was here yesterday.
Oh, I mean, please.
I'll share his pictures with you.
Please, yeah.
You can share it with him.
Sure.
This is Sumit Banerjee. Okay. Over to you.
Hi, this is Sumit Banerjee, and my topic is anomaly detection in fog computing system using optimization-based machine learning algorithm. So the background of the problem is like fog computing has emerged an extension of cloud computing to support low latency, real-time, and bandwidth efficient applications. And with the rapid growth of Internet of Things, like IoT devices, enormous volumes of data are generated at the network edges, making centralized cloud architecture insufficient for time sensitive applications such as smart healthcare, autonomous vehicles, industrial automation, and smart cities. The motivations is like increasing these things gives the motivation like increasing use of IoT devices demand low latency and real-time data processing. Centralized systems face bandwidth limitations and higher response delays. So the fog computing environment are vulnerable to anomalies, cyber threats, and system failures. And the research gap is existing anomaly detection approaches are mainly designed for cloud environment rather than fog computing systems. Key studies are like from Bonoma ETL 2012, we got introduced fog computing and its role in IoT environment. And there were some research gap which we identified, like existing anomaly detection systems are primarily cloud centric and not optimized for fog environment, limited integration of optimization algorithm with machine learning with adaptive anomaly detection. Existing methods struggle with heterogeneous and noisy fog-generated datasets. The methodologies so we divide in like three parts: research, data, tools, and techniques. So research design, machine learning based anomaly detection, optimization driven feature selection, real performance analysis, statistical and comparative evaluation. Like in the data collection, we got simulated fog computing environments, IoT device communication logs, network traffic records, system monitoring datasets, resource utilization measurements. Tools we used: optimization based machine learning, supervised learning models, deep learning approaches, real time classification models. These are the few results and analysis. So we got 93% accuracy anomaly detection with the fog computing system. Interpretation of results, like the experimental result demonstrate that proposed optimized based machine learning framework significantly improves anomaly detection performance in fog computing system. The accuracy we achieved like the accuracy of 93%, precision of 91%, recall of 81%, F1 score of 90% indicate that the system can effectively identify anomalous behavior while minimize the false alarm. And comparison with prior studies, earlier studies mainly focused on cloud-centric anomaly detection methods. Existing deep learning approaches often require like high computational resource unsuitable for fog devices. The purpose of framework combines optimization algorithms and machine learning to improve the efficiency and scalability. Compared to previous approaches, the current study achieves better real-time performance, reduced false detection rates, and improved resource utilizations. The framework demonstrates stronger adaptability to dynamic and heterogeneous fog computing environment. So the conclusion is like detection of accuracy improved to 93%, precision increased to 91%, reducing the false alarm. F1 score achieved 90%, indicating balanced detection performance. There are few implementation provides like a foundation for future optimization driven anomaly detection research, encourage integration of AI, fog computing, and edge intelligence technology, open opportunity for lightweight and privacy preserving disrupted learning frameworks. And the future scope is like extension of the studies, uh, integration of deep learning and reinforcement learning for adaptive anomaly detection, development of federated learning framework for privacy preserving distributed training, the lightweight optimization model for resource constrained fog devices. So there are still few limitations, like deep learning integration was limited due to computational constraint for fog devices. The framework may require higher computational resources for very large scale distributed systems. And these are some reference we used. Thank you.
Is it still from?
Four. Nitish Kudipuri.
You uploaded?
Mm-hmm. Around 2:57 a.m.
Today?
Yeah.
364 you said, right?
Yeah.
Link is sent.
Sorry, 2:32.
2:32.
It's the same.
No, it's come. You must have uploaded right now, no? Just
They want me to resend it now?
yeah, upload on this link. Or else let me check on the other link.
Oh, is there another drive link? I think I sent to Pranay.
You sent it anyway?
Yeah. So that's the drive he sent me where I have uploaded.
It was for yesterday's session?
No, it's for today afternoon session. I can send a copy again to Pranay.
Let me check it too. Can you upload it again?
Yeah, can you send me this drive link?
It is on the group. Let me do it.
So if you have his WhatsApp, I just sent him.
You put your paper in the same WhatsApp group, no?
This.
Someone share this link with me. Let me share the link again, right?
Copy link. Okay. This. Yeah.
You can upload it on this. Do you share the link?
Yeah, I shared the link again.
Okay. On the group?
Yeah, in the session chair group.
Session chair. Okay.
There's a lot.
No, it's okay. This is the one, yeah?
Yeah, should be done.
This group, right?
Yes.
Yeah. So,
yeah. Thank you, and sorry for the little delay. Good afternoon. My name is Ish Guripuri. First of all, thank you for the organizing committee, ICETM, to organize this wonderful team that could present their papers. So I'm an associate director of technology at Raymond James. It's a wealth management. Today I'm here to present paper ID 364, and the title is Mapping Cryptographic Transition Pathways in Post-Quantum Blockchain Systems. It's a multi-stage
mixed method investigation of structural dependencies. So coming to the introduction, so we've been hearing about the blockchain a lot, right? So blockchain is now the essential element of the secure digital infrastructure. So it powers cryptocurrencies, supply chains, decentralized finance, DeFi, that you have been listening about. And its security rests on algorithms like RSA and curve cryptography, the elliptic curve cryptography. So specifically, the 1994 Shor's algorithm can break the encryption schemes most blockchain systems rely on today. This makes transitioning to post-quantum cryptography both urgent and unavoidable. The challenge is that this transition is not simple technical upgrade. It involves a very complex interdependent set of factors, an algorithm selection, system compatibility and the scalability, regulatory frameworks, and stakeholder readiness. So regarding the literature here, a broad range of post-quantum algorithms have been proposed, hash-based, code-based, and blockchain multivariate polynomial approaches. But there are still some gaps here. The latest based cryptography has attracted most attention due to the balance in the security and its efficiency. Integrating these algorithms into existing blockchain systems is quite a significant challenge today. Scalability is still a concern because PQC algorithms carry large key sizes and higher computational overhead. But the broader gap is the absence of any integral multi-criteria framework combining DMATL and ISM to model how transition factors relate to each other. So this is a paper of the contribution, and we'll go over the methodology now. So what our research says is we followed a three-phased mixed approach here. One is phase one, the literature review and expert consultation with the specialists in blockchain, cybersecurity, and cryptography. This produced 10 critical transition factors, and the phase two is with the DMATL and analysis. Experts raised pairwise influences on a 0 to 4 scale. We built a direct relation matrix, normalized it, and computed a total relation matrix. And the phase three is ISM hierarchical modeling. We organized these 10 factors into 4 structural levels. The MAC analysis classified every factor by driving power and dependent power. So this is the methodology I was trying to explain, the DMATL, the ISM, and the MIC classification of variables. We'll go with the first one, the DMATL. Expert pairwise scores feed into a direct relation matrix on a 0 to 4 scale. Whereas for the ISM, we computed each factor's reachability set, antecedent set, and their intersections. Whereas the MAC, we plot every factor on a driving dependence map. Independent factors have been high driving power and low dependence. They are the root causes. So coming to the results and analysis. So what we have seen is the cryptographic readiness. The prominence is 8.92 and the relationship plus is 1.61. This is the single most influential factor in the entire system. Algorithm standardization, the prominence is 8.48 and the relationship plus is 1.29. Confronting to NIST standardization PQC algorithms is essential for interoperability. And the regulatory report, the third one, is the prominence is sticking at 8.35 and the relation plus is 1.33. So the table 6, the ISM canonical table shows the the base, the holes of P1, P2, P3, the reachability set covers of all 10 factors, and these translate into foundational readiness into operational capability. Level 1, the top holds organizational preparedness and user adoption. They are the ultimate outcomes of the entire transition process. So what's the discussion that is happening around these foundational drivers enabling downstream success? The central principle is mainly we categorized into 3 drivers: cryptographic readiness, algorithm standardization, and regulatory facilitation. They are the highest leverage intervention points in the system. When these are in place, the intermediate enablers activate, and system compatibility ensures the protocol integration, scalability maintains throughput, and interoperability enables cross-platform operation. And the risk management primarily mitigates the transition uncertainty. So overall, a secure blockchain ecosystem is what we are looking for, and business continuity, stakeholder confidence, and strategic advancement for early movers. So to conclude, what we are trying to go here is cryptographic readiness, algorithm standardization, and regulatory support are the key drivers for quantum resistant blockchain. These are the 3 root drivers that determine either the success or failure. The 3 capabilities the 3 base drivers influence intermediate technical factors, compatibility, scalability, and risk management, which then shaped organizational preparedness and user adoption. So the framework we have presented provides a structured dependency, aware roadmap from assessing current state through adopting PQC standards and executing migration to achieving a full quantum resilient blockchain ecosystem. So are we there yet? The financial services are not there yet, but we are doing a lot of R&D around this to make sure how can we apply it into the future blockchain capabilities that we are trying to approach for digital assets, which is going to be the biggest thing in the next 2 to 3 years. That's not for me. And so this is the future scope that we have actually put together. So the 3 extensions are planned: dynamic modeling, real-world use case studies, and live blockchain deployments, and hybrid PQC implementation blending classical and quantum-resistant algorithms. So our limitations that we found are based on expert judgment, which introduces subjectivity. It could change because that's how the research goes. Future work will address these through empirical validation and sector-specific studies in finance and supply chain. So these are the key references that I wanted to share with you. And once again, thank you to the ICETM committee, the IEEE Long Island section for giving me this opportunity. Thanks again.
If you go back to the slide before, please. No.
4?
No, one before.
One before, sorry.
The expert judgment, is that human judgment or machine judgment?
At this point of time, it's a combination of both with the data scientists and the data that we are trying to train the models. So it's a combination.
Machines that how and
I did not get the last part, sorry.
the judgment by a machine, right, by an LLM or
yes,
whatever tool you use for judgment by non-human.
Yes.
Would that be for what purpose and for what purpose?
So today, the blockchains that we wanted to play around internal to the firm is for the digital assets, and the core element is the data. And the data sets that we are training are coming up to a level which could apply for the traditional blockchains, but not for the quantumized blockchain. That's where the human is coming in and telling us, okay, we have restrictions. Maybe we have to look at and build something more scalable architecture with a quantumized one.
You're going to be connected with agent, human judgment.
Eventually, but we are not FOMOing on the So that's the main part. We are trying to be very cautiously optimistic of what we are doing. Thank you once again.
You said you have uploaded it, right?
Yeah, I think so.
Your paper ID is
194.
Let me check.
When I uploaded, there were only 3 papers there. There's only one database? I can see.
2, 3 database. I'm checking in all the databases.
14, there's 215 also. the
So
194.
should we start with 194?
Yeah, 194 is better. We won't need this. It's prepared.
Thank
you very much.
Here you go. Check.
Great, thank you.
All best.
Well, good afternoon, and I'm here to present 2 papers on content moderation. The first one is pretty straightforward, using LLMs to check the truthfulness or falsity of statements people make. And then our contribution is the use of multiple models and putting them into an ensemble so that you can make the determination of the falsity or truthfulness more robust. That's the first paper. Second paper, I'll tell you when I get to that paper. All right, so I think, there we go. So fact checking on the non-retrieval constraints, 5 models that we used for enhancing the robustness of the checking of the truthfulness, as I said. So people are using LLMs to tell whether something that's been published, a newspaper article, or other forms of communications, are people telling you the truth or not? And so content moderation, as far as whether it's accurate in terms of what they're saying. Many of those, the use of the LLMs are by saying, okay, let's fact check this and go out and look for facts that are out there in the literature if you don't know about what's inside your model. So if the model has some information, it could check its own information, but then the LLMs now with tools can go out on the internet and other sources and check. We constrained it in this case to not check outside, just take whatever knowledge you have in your training and just use that. So we started with that. That's non-retrieval, right? We're constraining it not to retrieve information outside. It helped us because one of the databases we used to check human coded databases, the PolitiFact one, it's out there, and if we don't constrain the LLM to do that, it will go out there and find the coding that a human gave it and bring it back and say, oh, see, it's not true, it is true. But it didn't figure that out on its own. It checked by what somebody else said that it's already been done. So we constrained it that way. And then we did it with 5 different models. At first, we just to see how each one, we were not intentionally doing this, but to see how each one would bring us back a result and see which one was more accurate. And then we said, well, let's put it together in an ensemble, council of experts, type mixture of experts type approach. And that made the results more accurate. So the ensemble of models made the results more accurate, which is kind of novel, and it gave us some interesting new knowledge. So we were motivated to enhance the work that we've been doing for some time in my university on content moderation by a number of students in association with the United Nations, for example, who chartered us to do some content moderation tools. And we've been extending it in other areas. So there are a number of studies that have been done, and we based our work on the fact-checking process that is used in the journalism. Specifically, the Tampa News has a PolitiFact process by which their journalists go out and fact-check stories and fact-check leads that they're pursuing. So we encoded that process, well-known process by which there's a six level classification of how true or false a particular piece of news or a statement that is made by a politician or someone. And I'll show you the methodology in a second. So there's not much work been done on using multiple models in an ensemble, specifically to try to undo blind spots that may occur by the use of any one model. If you use one model, there may be one of the categories where it does a poor job. But if you use multiple models, the others cover up for that. And so you wind up having a more robust answer. Similar to what happens with any ensemble, decision trees versus random forests, for example. A traditional approach to where you use random forests to try to improve on the accuracy of analytical approach. So what we did is we tested 5 different frontier models, and I'll show you them in a minute. And we asked them to, here's 100 statements that have been made. We have the human coded answer. So we have the gold standard ground truth of those statements had already been fact checked by humans, the journalists who pursued those statements. They're in a database, a well-known database. It's called the PolitiFact database. And there's 1,000 statements there. So we randomly extracted 100 of those and used those as our testing data to see how well our models would do. And we constrained the models not to go out on the internet to look for the answer, because they would have found that database out there and brought back the answer. Right? So we were very careful there. So the PolitiFact scale is true, mostly true, half true, false, and then pants on fire. You've probably heard of pants on fire. That's an expression that's made, but they have that as a category. It's so far out there in falsehood that it is just amazingly false. Interestingly, where the models tend to fall down is where there's ambiguity. And you can tell in this scale where that ambiguity would be, right? Half truth. But by using multiple models, it turns out we can actually overcome that problem. So we tested, this work was done about 6 months ago. The models have moved on. So you're using model versions that are, at this point, 6 months later, kind of old, but they were all at the same level with each other. So they were all ranking, they were the top models at the time. Right? Gemini 2.5 and ChatGPT 5.2, Claude 4.5, and DeepSeek and Dubao. My colleague, I wasn't keen on using Chinese models, but my graduate student, my colleague, was Chinese, and she wanted to introduce them, and we did. And it turned out to be a good thing because those models seem to be robust in finding answers. I wouldn't have thought so, but they were, unbelievably. So we used identical prompts in each of them. And you have to understand that some models, like Gemini, makes up its mind how it's going to interpret the prompt. You have to tell it specifically to follow the prompt. Otherwise, it starts, by the nature of what Gemini does with DeepMind, it wants to do things its way. And it turns out it starts finding its own approach. It may even redefine things from what you said. So, but in this case, we just used the same prompt, all of them. And we didn't tamper with their temperature. They were all pretty much set at whatever temperature came out of the box, right? We could have probably set it to, mess with the temperatures, but we didn't, and that was fine. And again, no external retrieval. And we then looked at the results and compared them, inter-rater comparison, as normally would do, with an accuracy score, F1 score. We did those kinds of tests. And we actually found out that Gemini, DeepSeek, and Dubao were better than the other two, amazingly. And we then did a three model majority ensemble. And okay, good. And it turned out that those three gave us a much more robust, as you will see from the answers. Okay, so accuracy range wasn't that great, but it was good enough. From anywhere from 0.3 to 0.4, macro F1 0.2 to 0.37. Again, not fantastic against the human coded data or the scores. And you have to remember we have 5 levels here, so there's quite a little bit of ambiguity. And the highest score was, interestingly enough, DeepSeek, with a F1 score of 0.732. I wouldn't put too much emphasis on that, but it is. And interestingly, Claude had the weakest performance. Go figure. Now, you could see that the half-true is where the problem is on the table on the right. The half-true is where the problem is. And when you do the ensemble of the 3 best performing models, Gemini, DeepSeek, and Dubao, you get it to vote, and you get a result that compares fairly well across all 5 levels with respect to the human coded data. And so we were pretty happy with that, and that was our discovery, so to speak, that it was good to put the ensemble. In retrospect, being that we're doing a lot of work with council of experts or mixture of experts models, that made sense, right? And the work that in machine learning, where you take ensembles to try to get a better performing algorithm, that seems to work as well. So we were pleased with that result. So that's basically our finding and our presentation to you. We ensemble, it makes for a better model, right? And no single LLM was reliable enough. You can see from the table, it's hard to pick it out from the table itself. There's a lot of numbers there, but they're all uneven across all of their judgment of the same 100 statements, whether they're true, not true, half true, pants on fire, and so on. And they were all, we picked, they were random, but we made sure that there was a representation of each of the 4 categories across the 100 statements sufficiently so that you could see a result for each of the categories by each of the models, right? So that was a pretty good result for us, and we're happy with how it turned out. Okay. Now we want to go ahead and do a little bit more, maybe further testing with more than 100 statements. You have to do the statements 10 at a time, because if you do all 100 at once, the models, they go very fast and they don't do as good a job. So we discovered that if you did them all at once, your results were very poor. But if you're asking it to do 10 at a time, you chunk it that way. The models take their time, they go through it, they do more thinking, they do a better job. So it takes time to do these things, to have that many, but it worked out really well. We're very pleased. Okay. So we want to go beyond the 100 statements, and we wanted to try to optimize these models, go forward and see what the newer models will do. But there are many more things you want to explore and test, so we're not too sure we're going to continue with this. Okay, and that's the references that we used, specifically the reference to the PolitiFact database and the process.
you give us please an example of one statement that we use and how was the result of the models by model?
Yeah, that's a great statement. Some of the statements are scientific statements. So the earth is flat, absolutely false. We'll use that in the next paper as well. Yeah, one of the statements. So we'll see where they're and of course, all the models got that one right, because that was pretty straightforward. You have to realize they're relying on the internal learning, the internal training. Right? So for sure, scientific data would have been in their training models. Those advanced models, they were pretty advanced. So you would have thought that they would know that the earth is round, not flat, and they would come back to that conclusion. So that one was pretty easy to come out. We used, and I'm not going to quote because I don't want to get into political debate, but we put a lot of statements were made by our current president, and that some of them were pants on fire, by all the models, right? So, but it's interesting. The ones that are interesting are the ones that are in the middle. There's nuance. Is it true? Is it not? But I don't recall one. Right. Yeah.
So the fact checking that you've performed, right?
Yes.
Are those on the paid subscription models or just the basic free tier? Because
I see. Yeah, no, good. We used wherever possible. We had a subscription, so we didn't use the simple surface model that you get for free. Yes, make sure we had the subscription. So Gemini NYU subscribes because it gets all the students the pro version. For ChatGPT and for Claude, I had an account, so my student used my account. And the other two, they're open source, right? I don't think they have subscriptions.
Yeah.
Dubao and DeepSeek, right? So we use whatever they provide as the most advanced model. And then we put it into the thinking mode as much as possible. If those were available at that time, I think they were. They were just coming out with ability to go from surface to thinking mode, which did a lot more logic thinking through, right? Good? All right. Thank you. Now, you want to set up the next one is a little interesting. So in pursuing
You have traveled today, right? You have traveled. You have come from New York? Or
Yeah, go to New York, yeah.
Yeah,
I travel on the Long Island River. But I don't think I will be going back because there's a fire at Penn Station.
Oh.
Yeah. So I get notified there's a fire at Penn Station, find other means of transport. So I'll go to Jamaica Station and take the E train to Manhattan.
Hopefully that's right.
When Saturday, right? Saturday. So it's good that you didn't have it on Saturday or something. But they're set. They're okay. So interesting that because of the work we did with the UN, she's setting it up. Okay.
That's your second, right? That's the second one?
That's correct.
Over to you.
Thank you very much. So this one is a little different. It's still content moderation, trying to check to see what people have written or what they say. How true is it? But there's a nuance here. The use of epistemology. Okay. So institutional discourse. Organizations put out press releases. They put out financial statements where the organization discusses the results that they've had, right? They put out advertising, marketing material on their website, right? And then scientists write papers like we do, our papers, textbooks, memos that are generated internally and circulated. Some are done by the CEO, some are done by staff, right? And you want to know, okay, not only whether the material in there is true or not, how much of it, but we want to go beyond that and say, how are they using language to try to convince you that what they're saying is true? So things that, for example, power washing, using your authority, your position of power, to then convince everybody else that they should follow what you're saying. The perfect example is the hippo. You know about hippos? Highest paid person's opinion, right? CEO walks into a room and everybody waits to hear what they have to say, and his opinion counts more than anybody else. So often that quashes debate by what just he says it, because he is, the person in authority. He's responsible. But in reality, he's also the person who's responsible, who has the highest risk. If things go wrong, right, it comes back on him or her. So people wait and say, well, you tell us what to do because you're taking the risk, boss, right? So, but they tend to quash debate, which is a problem in the sense that if you want to hear other opinion that may be useful and important, they don't surface because your opinion squashes the debate. So that's the kind of thing you want to catch how people say it and what are the circumstances upon which they say it that add nuance to whether what they're saying is just as true or not. That's what we call by institutional discourse, whether spoken in a meeting or written, and we want to analyze it from the point of view of epistemology. What are they saying? And we use various philosophers to analyze that, as you will see, right? And then tell what epistemologically is going on to see whether there's a fallacy there that's being pushed without you knowing it. So going beyond, is the claim accurate, which is the basis of the last paper, to what kind of claim is being made, what evidence they offer you to support that, are they using authority in a proper way or not? For example, the authority of a scientist who presents a paper, he does it in a way of saying, I found these facts, I take it, I all right, sorry, no problem, right? So is the language used in a way that they're saying, here's the facts, but I'm open for you to challenge me because we're in a learning environment, or no, I'm the authority, you better keep quiet. For example, facts as presented in a scientific paper are open for challenge, right? The Karl Popper falsification, his theory of science that says science moves forward by all theories being falsified, new theories being created. So the scientists should be subscribing to that mode and be open for challenge. But as soon as things get into a textbook, now the textbook, the author is the authority, and the people reading the textbook they don't have a way of challenging what's in there. They have to learn it by the way the authority put it into the textbook. Now it's starting to get more, you learn this stuff because I'm the authority, I'm telling you that you have to learn it. And this is the right thing, right? So by the time it gets into a textbook, for example, it's already unchallengeable. And you go all the way through to articles of faith in certain religions where you can't challenge authority anyway because it's hard to challenge it, what facts you're going to bring to bear. So these are the levels. So you got the analysis of that. Is this a religious faith item? Is this a textbook? Or is this a scientific proposition that people are thinking, think about it this way, there's some data that supports it. Maybe you accept it, maybe you don't. It's up to you to use your own judgment, right? Those kinds of analysis. So organizations, they put out stuff, and you can check whether it is true or false using fact checking. But beyond that, you want to go and say, how are they saying this? All right. So it's important for governance. It's important for explainability of tools. It's important for human review, right? Beyond whether it's true or false, whether the program has a bug, or was this program written in an elegant way or a very, not so elegant, right? That kind of thing. So we produced our first cut of a tool that helps us move in that direction, right? So the major philosophers we use for epistemological analysis, first is Wittgenstein, that teaches us about how language is used. Mostly is how people use language to communicate and try to convince other people about what they're saying. So Wittgenstein and his methodology is embedded in the prompts that we use to develop this engine. Popper is the other, is in terms of the person who's presenting this material. Are they open to have their material challenged with facts so they can be falsified or not, right? Falsification. Scientists are trained to accept that until, of course, the scientist becomes so well known, he's a top figure and whatever he says goes, Linus Pauling will say, you got to take vitamin C to cure the cold. Well, he didn't do any experiments on that, but at least he was proposing it. So because he was a Nobel Prize winner and, his words count more than anybody else's words, that kind of thing. Arger is about the learning organization. Chris Arger is fifth discipline. And whether you're open to learn, right? And is your language saying that maybe we were wrong, tell us, and we're open to be corrected, right? Is your language, are you using language in a way that allows for that opening, right? To say, hey, some politicians tell you, no, you do it my way. And I'm always right, even though they're wrong. And so you can't challenge them. They're not open to learning because they're not introspective. And we get in trouble that way. So there are a number of other situations. And the last key study that we have is there's a very well-known database, Mafalda, that has lots of, it's a corpus of human-coded text on how accurate or inaccurate these statements are, right? So it doesn't cover what we're doing in terms of using epistemology to analyze, because as you'll see, we cover other dimensions, but it gets somewhat close to that. And we use those statements to at least validate our model to give us a baseline of, can it tell truth from fiction? Can it tell truth from falsity? At least that, okay? And then we presented the engine, and I want to discuss with you how one validates those aspects of the engine that are epistemological. So, right now, there are no systems that directly audit institutional claims that are made, especially in the way language is used. Fallacy detection doesn't cleanly match how we want to interpret what people are saying, how people are saying it. Right? And if you use humans to do this, as with any qualitative analysis of text or any form of textual data, it costs too much. You can't do a lot of it. You want to do it at scale, right? So this is why we want to use LLMs to be able to process a lot more text than a human can do. So the other is that LLMs do a pretty good job, as you saw from the paper before, checking whether things are true or false, but they don't always logically follow to the end result of an analysis. So what we did is we built a prompting system for an LLM, still a prompt, that has a number of gates that you take a text, you bring it in, and you analyze it. First, you extract the text in a form that could be analyzed by the LLM, and then you check it against Wittgenstein and say, how people are using language, what form of game are they playing with the language, right? Along the lines of Wittgenstein's construct. And then you say, well, are they speaking in a way that they are open for challenge? Like Karl Popper tells us, falsification. Are they laundering their authority? And in other words, are they using their authority to push it down your throat? Right? Or are they saying, even though I'm the authority, I'm open for you to challenge me and let's have a discussion? More of a Paul Freire, using the other person and elevating them to a peer rather than you're the authority and they're the person that has to be told what to do. And then arduous, are you open for learning in case you may be wrong, or are you just so entrenched in your own opinion and belief that you're not open for learning at all? So we look at those cases and see how is language used and analyze it. And it worked out very good. And we then map it in terms of, are they using their head? In other words, they're trying to convince you from a mental point of view or from an emotional point of view. And then are they trying to disrupt you, or are they trying to keep the power, the stability? So are they trying to keep the status quo, or are they trying to foment revolution? So there's two axes, right? What are they trying to do? Whip you up into challenging the power or supporting the power structure. So we took a number of texts. Some of them came out of this human-coded database, Mafalda. And, oh good, goes away. And some of the others, we wanted to see how people were expressing themselves in the business world. So SEC filings, right? A 10K or a 10Q, which is the company's not only factual accounting of their numbers, how they're doing financially, but also their interpretation of how the company did, right? Because they're producing those for the public who's going to invest in them. And how are the CEOs washing mistakes and where are they hiding their problems to try to keep people from keep investing in their company, for example. So we wanted to see and analyze things of that nature. Journalism in markets such as energy and oil that sometimes are prone to be misleading, right? The only problem we have is that the only human-coded data that we have so far is just the true or false from Mafalda. We don't have, we haven't to validate our model, right? We could create the model, we created the model, we checked it in, it appears anecdotally to work, but we don't have human-coded data yet for the deep epistemological work. And that's what we hope to do next. We also used two models, GPT, ChatGPT. Compare the two, came out pretty even. Neither model was better than the other. And then we used Cohen's Kappa F1 score whenever we had some human-coded data as the ground truth. But we saw that the LLMs didn't always catch on to the epistemological analysis that needed to be done. They don't quite get Wittgenstein. They don't quite get Popper. So we noticed some holes in there. So that's our finding, is that in general, it works. We can analyze these texts of various forms for those aspects of the use of language and the way people are trying to express themselves beyond whether it's true or false. But the models are still too rough. Maybe as the models get better, and we hope to do this work maybe in a year from now to try to update it, they will get a little better, but we did notice that some what we call kernel violations, kernel, a basic way of analyzing along one of these dimensions just didn't quite work on some of the texts as we were expecting, right? That's what we meant. Saw that. But we did pretty well with a number of types of texts from various sources. Some we did synthetic data. We created news articles by taking an LLM and saying, okay, here's the situation. Write me an article for this type of newspaper and make it neutral. And then write me this article, same facts, but now make it a little bit more inflammatory. And then make it really inflammatory, right? So we use that as synthetic data to test a content moderation tool. We built another tool to check whether the writers were being inflammatory or not, right? And so we use that data here to see whether our epistemological tool would pick up on that. And it did. It did a pretty good job. Every one of those where we had coded the text as neutral, a little bit biased, somewhat, quite biased, and then just super biased. So the texts were all coded like this. 4 versions of the same story, written 4 different ways with a lot of bias or very little bias, and my tool picked it up. We did that with a number of these synthetic data sets. And then it turned out that it does a pretty good job, but it does have some problems. Not all the LLMs fail, they fail on occasion, and we don't know why certain failure modes appear. Yeah, I'm going to finish now. It's going on and on, right? Yeah, it's okay. You get the point, right, of this thing. So we did have some violations of our model. Our models were violating some of the situations, and we need to explore that a little bit more. So in general, we have a tool. We're happy with it. It analyzes and classifies a text as to whether you're being exhorted mentally or emotionally, and then are you being told to support the status quo or disrupt the status quo? Those are the 2 dimensions. And in general, from the text that we used, we could tell that the model picks it up, both types of models, and the GPT and the Gemini, ChatGPT and Gemini. So we're happy with this. It's a beginning. It's imperfect, but it's a good indication that we should pursue it further. We like the 4 dimensions, 5 dimensions that we use, Wittgenstein, Popper, Argyris, and so forth. We're going to extend it to do more and find more human-coded epistemological situations that will help us validate the epistemological side more than just the true-false side. Good? Questions? Good. Thank you for the opportunity. Yeah. And the next paper.
Thank you so much. And how many presenters left? 1, 2, 3, 4. We request all of you to be complete your presentation in 10 minutes.
Yeah.
Right?
10 minutes.
It's your presentation now?
Yeah. 154.
You have uploaded?
Yeah.
Right. Okay. Should I go for more copies? It's okay. It's there.
Yes.
You forwarded and you deleted. It is on link, so you got deleted from them. This is your presentation, right? Okay. Over to you, Rahul.
Thank you.
Good afternoon. So I am Rahul Modi, and I am going to present today something related with the Gen AI. Everyone is adopting, enterprises are adopting a Gen AI, but no one is talking about much secure about the security model. So here I am come up with the idea with the security model with the multi-tenant architecture on Azure with the Gen AI. So the background is as we know that enterprise is adopting Gen AI on a cloud. Especially, I am talking about the Azure one right now over here. And when we see the cloud model, when we implement the cloud model, many of time that the security wise we are not thinking much, and the data are very sensitive now nowadays. And when we connect the cloud model with the any of the Gen AI LLM model, that makes more we need to take care about the security. Some like prompt injection is now it's very much common, that makes the flow or agentic flow disturb and bring the data from there. The one of the key study that I talk about, that introducing prompt injection, how we can avoid it, how we can make the multi-tenant architecture allow with the cloud model along with the Gen AI. So consider a flow that I have a data secure in a somewhere in a block storage, and we are bringing the data from there. So it's a private network that we are bring the data. But what about when we do some agentic flow with the getting the data from the outside world, some latest data? So at that time, that prompt injection is playing a major role right now to bring the data and disturb the agentic flow. So for that, we have infrastructure how we can set up it. In our next slide, I'll showcase. But here, one of the gap is there that it is limited to right now with the Azure. In the next paper, I am coming up with the multi-cloud model as well, where AWS is also going to support, and the OpenShare as well. It is going to support. How we can do this one? So cloud model, let's say we are doing a containerized with the Azure Kubernetes services, and along with the Gen AI workloads. The second one, we can configure the RBAC model, VNet isolation, when the data are passed, we can pass with the security keys. The authorization security keys seem like let's say Azure function. If we are calling it, we need to pass the Azure key. So that way we are authenticating the your any of the data calling model, or we can authorize the data are the requests are coming from the authorized mode. Uh, so major key finding over here that 100% we are cross tenant isolation enforcement that we are doing it. So when we are dealing with the multiple tenant in a single application, that comes with the 100% cross tenant, the latency over here, that throughput that we are achieving over here, that 95% request per second. The same way, isolation success rate is 100%, and the latency overhead is a 6.2% RBAC, and that we are making the secure each tenant, each user over there. It's not something like it's the first time that we are introducing some model or some architectural flow. It's already been designed by the couple of other research paper, but on top of it, that our research paper are doing some extraordinary output among the two already exist, which I have taken the reference as well, or for both of it. Let's say who are focusing the multi-tenant, that paper 1 and paper 2, which is already is there, but it's supporting the partially. We are strongly here multi-tenant that we are supporting it. Same way, the agentic workflow or specific thread with the GenAI model. So both the model has the conceptual or the limited scope, but we have tested and configured in our enterprise architecture as well. So this way we are pretty sure that comparison wise we are heading of the other two papers. Conclusion. So I'll showcase something. I can showcase something how we can configure the total flow, end-to-end flow. When we can design the infrastructure, it comes up with your RBAC model. Once your RBAC model done, so it's called as a identity first model, and then come up with your infrastructure part. Once your infrastructure is ready, that infrastructure is come with the VNet isolation mode, and then it comes your containerization. That containerization help us to deploy in a multi cloud model. Right now it is only for the Azure oriented, but yeah, we have used the containerization. So pretty soon that next paper or the next version that we are going to do it for the multi cloud. The fourth step, it is coming up your API or your function level security model, that each function are going to authorize and authenticate. Fifth level is coming up with the log analytics. So that comes with the logs. So right now, each AI things or agentic AI things are doing their automate the performance, but we need to log it. We need to log each and every activity. Are they performing the correct way or not? That we can determine with the logs. So logs is very much useful over here. The future scope that I told you that we can increase the scalability on a production, multi-cloud adaptation. That right now it only Azure oriented right now, but it is going to also allow for the AWS as well. And we can also more go deeper in a AI based or automate based security governance. Some of the key references over here for the Microsoft has just launched that multi-tenancy on a 2026. Same way last time he launched on a 2025, and before it the first time ever Microsoft launched on a 2023. So these are the three major references in my paper. Even the IEEE cloud computing and the security privacy, it's one of my key references for the security model. And the third one is one of the book is there with the prompt injection, and that we have heavily used in our model, that preventing the prompt injecting from the outside the world. This is what from my end. Any question? Thank you.
Yeah. Yes.
Let's do it on full screen. Oh, what's that? Good to go.
So my name is Leonardo Kanyamanamaya, and I'm a master's student from the Center for Research and Advanced Studies of the National Polytechnic Institute of Mexico. And here it is. So my project is in relation to control theory, and it deals with digital systems. So what happens when you're working with a digital system is that in order to properly control the system you're working with, you have to take into account the sampling period. And there are certain systems, especially for systems like the embedded or the network systems, where you can't always guarantee that you're going to have a regular sampling period. There will be occasions where it changes. For example, if there's a data loss when you have a networked system, or if the most optimal way to communicate information in the system requires an irregular period. But when you review most of the solutions that have been developed for this problem, the vast majority of them require you to have an accurate model of the system that you're working with. So what we tried to do is to develop a solution that doesn't require the model. And for this project, these three papers were the ones that were the most important for its development. The paper by Drs. Tusait Dayapun and Luatrangjit form the base of the controller in this project, and the techniques from Ho and Jin were used to adapt the controller to solve the issue that we're working with. So what we did to solve the problem is the FREN is a controller that uses fuzzy logic and automatic learning techniques in order to allow the human intuition to be better adjusted online with the controller. Because this process doesn't require the sampling period in the control or the learning law, the only adaptation that was required is to make one of the terms in the learning law for the fuzzy rules emulate networks to be model free, which can be achieved with an approximator that was taken from the work by Ho and Jin. To test the performance of the controller, we created a simple system that we connected to MATLAB in order to be able to measure the performance of the controller. So here is the pseudo-partial derivative. This is the term that requires the model of the system in the original controller. For the most part, the estimator itself is unchanged. However, the resetting algorithm has been modified so that rather than using a constant, it resets to a previous value in order to account for when a system has multiple steady states for the pseudo-partial derivative. In order to ensure that the learning law and the controller is stable, we took a look at the system to find its stability in the Lyapunov sense. And we can find that when our delta V of k is a negative value. When we get into the actual analysis, we find that there is an ideal case and the practical case. In the ideal case, we can assume that the actual value of the pseudo-partial derivative will be the same as the one being estimated. When this is true, the equations, they simplify quite simply. And what we find is that the terms will always result in a negative value for delta V of k, so that in our learning law, the only restriction is that the learning rate has to be positive. In the practical case, where we don't assume that the estimation is the same as the actual value, we find ourselves having yet again another set of two cases. In the first case, where the signs of the estimation and the actual pseudo-partial derivative are the same, the analysis is very similar to the ideal case. And so you find again that the learning rate only needs to be positive for the system to be stable. However, in the case where the signs are different, you find that you have an upper limit, which is defined doing this graph here, which uses only the estimation of the pseudo-partial derivative and the output of the associated member function. So the performance of the controller on a system with no perturbations or modifications to the sampling period performs really well with almost zero tracking error. When we added a low variation, the performance of the controller holds up very well. But where you can most see the effect of the design of the controller is when we add a high degree of variation into the sampling period. In this case, the tracking error only gets a little bit fuzzy, but still remains very close to zero values. So we were satisfied with the performance of the controller, and it showed that it was able to rapidly adapt to the systems that it was being applied to, and was minimally affected by the change in the sampling intervals. And the controller, for the design, very few assumptions were actually made. And so it should be applicable to a wide variety of different digital systems. There were some limitations and some improvements that need to be made to the controller. When the pseudo-partial derivative reaches zero, there is a tiny error introduced around when the reference reaches to zero. In my testing, what I found was that for a signal with a maximum amplitude of 1, this error came out to around 0.02 volts, something very small. Due to time constraints, we weren't able to add a comparative analysis with other controllers, but we would be looking to add something like that in in the future. I would like to be able to apply this controller into a real system, into a real problem, in order to get a better idea of how the controller will actually behave in different circumstances. And these are my references. Thank you.
Thank you. Any questions? Thank you. request everybody to kindly wind up your presentation in 6 to 8 minutes. Yeah. You uploaded paper number?
Number 6. I think it's a little bit at the very top.
Paper number 6?
Mm-hmm.
You uploaded?
Yeah.
This is the paper.
Yeah, that's it right there. Okay, I apologize. I have to be very, very quick because I do have to go. So I apologize about that. But I'll tell you in a nutshell what we have been doing. So we've kind of developed. We've developed this algorithm. Essentially, we call it the reservoir computing, right? And so I know we're going to go to the full screen here. But essentially, the idea is that you do AI in parallel, right? So you do LLM versus LLM versus LLM, and then you do all of it together. Then you assemble the final result. And what we have been doing, we've been applying the algorithm to a lot of different things. So in this case, we actually applied it to encryption. So if you look at all these different systems that we have out there, you have your computer, you have your Internet of Things, right? You have your phone, you have all sorts of, even toothbrushes today are on all sorts of I think this is still working. Yeah, even the toothbrushes are now using IP. And so the idea is, well, how do you start encrypting this data? Because anybody could actually hook up to your stuff and start actually looking at your data. So what we have done is we've taken a reservoir computers, so LLMs in parallel, if you can think of it like the AI in parallel, and we started using chaos theory to actually encrypt all the traffic, reassemble, then decrypt it, right? So that way, if anybody captures your stuff, they can't actually tell what it is. I'm not going to get into all of this, but essentially what we have done is we've compared it against AES and RSA's algorithms as well, just to make sure that it actually works. So the idea here, this is a mathematical foundation for this, is this is going to be your input function right here. This is the input signal. But then we kind of, the way we build it is we want to make sure we have alternate, and we can actually control what is actually being put in. And that's how we have put in this, developed these equations. And then from there, we can start putting in the noise signals, latency, some other things, right? And I'm just going to go right into our results here. So a bit error rate is a really interesting metric that we have in here. So essentially, how much error do you have versus the signal to noise ratio? And the interesting thing about it is the error rates are actually smaller if you do reservoir computing versus if you do some of the other things. So even if you had a lot of noise, if somebody's trying to jam your toothbrush or whatever may be the case, you actually still have really good data rates. The other thing that we notice is that whenever you have Wi-Fi internet, you start dropping certain bits, right? You never get all the packets. So certain packets are actually being dropped. So the signal to noise ratio increases as you start dropping more and more bits. You increase the signal noise ratio, but the error bits are still going down. So the RCs actually, if you can actually use parallel AI, I guess if you call it, then you can actually have a much lower signal ratios and still have the same output. Now, the other thing that we've actually have done is how much energy does it use. So like if you have anything like a toothbrush or anything to your phone, you don't want the battery to die. Well, how much energy do you actually use versus the encryption? Every time you put encryption on things, you're obviously using a lot more compute power, a lot more energy and other things. And what we've noticed is that the RC actually behaves much, much better, right? So the reservoir computer versus AES and Lawrence KS, which is an RSA we've actually had out there. So the energy consumption is going to be much, much smaller if you're actually using the RC. And that's a really interesting result that we actually also got. So it's a lightweight model, if you will, to actually encrypt a lot of your stuff that you can put anywhere, on anything that you have. And then the other thing, the sensitivity. We started putting different variables in there and just measuring different sensitivity. So the models are extremely sensitive, which is kind of a bad thing, I think, because every time you want to change some parameters, the models are pretty sensitive. And then the last thing that we have looked at is the actual latency. And so the latency on the reservoir computers is slower, which is naturally which is what you expected, especially if you have a lot of them working in parallel. AES, this is arguably some of the better ones. The 128s we've used. I think 1024 is the highest when we pushed on the actual AES, and the latency obviously is much higher. So maybe a little bit better encryption, but also higher latency. So anyway, so that's kind of the gist of our research. So the idea is, and I'm going to open up the questions. The idea is you want to encrypt your traffic on everything, right? So nobody can read your stuff, and you want to make sure you don't have latency and still not use a lot of energy. That's where the algorithm was actually there. I do got to run. I really apologize about that. So, but if you have questions, please email me. What's the last? You know what it is.
The last presentation.
I apologize about this. Yeah. Oh no, I think I'm. Oh, wait, do I have to like talk? So I feel really this.
This was yours?
No. You said stop screen, right?
No. I thought. Is it your presentation or no? Still, yes. Be very quick, right? This is yours? Okay.
Okay, my name is Lakshmi Narasimhan Krishnamurthy. So I'm going to present AI-driven workload management for multi-cloud and edge computing environments. And these are all my co-authors. So we are here to discuss about the main purpose, the workload management distribution system. So what we have currently is a lot of challenges, and so we are going to address in this introduction and the challenges of modern distribution computing. So what we have right now is like we are seeing the widespread adaptation of multi-cloud complexity, managing workload across the heterogeneous platform, introducing the critical complexity. Enterprise leverages multiple cloud platform to avoid vendor lock-in, but face challenges in data transfer, latency, and SLA compliance. So the real world, when it comes to the real world, the data transfer and say, for example, work distribution and UPS and all those things, it gets like a lot of time when we are in the festival season. Say, for example, Christmas. So if we send gifts and it takes a lot of time to reach the other person, the families and friends. So that still we think that we are having good network and all those technologies that we have, but still it faces a lot of time. And when it comes to like um, and then the second layer is like edge computing, so that has its constraint. So pushing computation closer to data sources introduces limits in processing power as well as energy. So real-time demands render traditional static scheduling mechanism fundamentally inadequate. So that's how we have to introduce the AI. So the solution from AI is like AI-driven framework analyze resource states in real time to determine optimal workload deployment across cloud and edge nodes, ensuring flexibility and efficiency. So what right now we see is the research gap. And cannot adapt the real-time changes in the system state. And then right now we have the scalability issue, and we have the multi-layer coordination issues and the data quality constraints. So machine learning models can need clean data, but real-life world data is often messy. So as we all know, and explainability and security So AI-powered system raise concern about model transparency, data privacy, and vulnerability to attacks. So that's why we need to have like data with some encryption. Our research objectives are simple. It's like 5-step process. So we are proposing an intelligent workload management system. So integrating machine learning, and then deep learning, reinforcement learning, and anomaly detection, and then developing a predictive model, and then I implement a reinforcement learning based scheduler. So the next step would be like incorporating anomaly detection to improve systems reliability and fault tolerance. The next step would be evaluating the proposed system against traditional scheduling strategies. So in our research methodology, so right now we have we are using quantitative and experimental methodologies centralized on a simulation-driven system. So we are leveraging machine learning and optimizing workload planning techniques to reallocation. So we are introducing Q-learning. Here, so the bandwidth and the energy limits are often compromised. And then AI models, the AI model components, so how we are using the system to learn and adapt. Here, if you have seen, say, for example, that the predictive model is 92% accuracy. And before this, I was like, mostly, I don't know, it's like in linear regression in short path algorithm. So, for example, you have seen like the circles, the lines, and then other circles. So you see that's like the shortest path algorithms, nearly like the KNN. So we have to see what's the nearest path and everything. So we have all these techniques, but still we fail on the festival season, like say for example, say for other seasons like the New Year and everything, but still we are facing a lot of issues. So that's why we are introducing these AL models using MLDL and reinforcement learning. So using this, the predictive model, and right now we have like some real-time models and the simulated models. So it's not like 100% real-time models. So we have like 90%, 95% accuracy, and using this reinforcement scheduler. So we having that 0.95, and the anomaly detection is like the grade 91%. So from our analysis, we have concluded that the average latency has been reduced and the throughput has been increased. So with our findings, we have that the predictive model accuracy of 92% and reinforcement learning reward convergence, it's 0.95, and anomaly detection, F1 score is like 89.5. So in the graph, you can see all these things are improved drastically, or at least by 40-50%. And the implication that, yeah, as you can see, the cloud architects, edge deployments, energy sustainability, and yeah, and so on. So by concluding this, including AI in our real life, like workload management system has decreased 37% latency, and the faster recovery of 60%, and the throughput boost by nearly 40%, and the gain is around 30%. So the future work that we have seen, it's like we have to include in the real life data, the large real life data. That's one main thing in the future, and that's about it. Thank you.
Thank you so much. Next paper, we have one co-author online and the author is here. So, Gunjan, can you tell me the paper number, please?
It's 146.
And can you please come on camera, please? 146, you said?
Yes.
146, right?
Yeah.
146.
Oh, you're still there? Are we there?
Rahul, this is a
Yeah,
paper, right?
sorry.
Yeah.
Is there a lag or something? I cannot.
Hi, Gunjan. Good to see you online. Gunjan, can you hear me?
Yeah, it's coming as a lag for some reason. I mean, is
There's
there
a
an
lag, yes.
Yeah. Suddenly there is a lag. I don't know why.
Gunjan, can you log out and log in again?
Oh, yeah, sure.
Meanwhile, we can take other presentation. So what is your paper number? 2? 350. Why don't you come first? Few researchers are very emotional for their work. They want to present themselves, no? You said 350? Yeah. This is a paper? Yeah. That's your presentation, right? Wonderful. Over to you, Shreya.
I hope I'm like visible. I'm a little short. Okay, great. So today I'm here to present the paper Working Hours, Workplace Communication and Productivity in the Age of Artificial Intelligence. It is a cross-national industry perspective looking at 6 country comparisons. And yeah, first just going over through quickly of why we took this study. There is a growing national debate on the kind of suggested longer extending working hours in India and kind of comparing that to the productivity that we have. And this was triggered by comments by very famous business leaders. But we also see India presenting a paradox, which is that more working hours do not equal more output and more productivity. And India is amongst the top 5 economies, and that's why it is really important to consider this gap and understand it better. Going over the productivity paradox, so we kind of learned that India works more than any country at 8 hours per year, but India also produces the least per hour. And compared to Germany, Germany works 650 hours lesser per year and earns 8.6 times India's rate. And even 67% of Indian employees reject that long working hours, the idea that longer working hours equal more output. So the real issue that we see here is not about effort, it is about how work is organized and being rewarded and evaluated in India. Past research kind of not looked at India in a very cross-national productivity research. No study has also kind of looked at IT, government, healthcare, and education sectors together. So this kind of became important for us to fill the gap. Work-life balance is also not seen as a mediating variable, kind of just seen as side outcome, which we also wanted to discuss here. And the role of AI also seemed really important to consider since that's a growing part of our workplace environment. A little focus on the role of AI. We do see that it helps people work faster and smarter in workplaces. However, it also introduces different kind of stress and also enables more blurred work boundary lines between employees. So it was important to consider that as well. Oops. So 4 research objectives that we had, first was just mapping the work hour patterns across government, education, healthcare, and IT in India, and then using those patterns to quantify the relationship that the working hours, work-life balance, and self-rated productivity shows. Third was just comparative understanding of India against the 5 nations using the ICETM 2024 and OECD productivity indicators 2024. And the last objective is the more long-term goal of enabling more policy recommendations while understanding the sector-specific productivity in India. Oh my God, this is... Okay, so covering the methodology, this is a mixed methods sequential explanatory design. The primary data was collected through an online survey. The respondents, we had a sample of 169 Indian employees. The survey was conducted between February to April 2026. The survey had a 22-item questionnaire with using 5-point Likert scale, both measuring productivity and work-life balance. And the secondary data, as mentioned, was used from the 2024 ILOSTAT and the OECD productivity indicators. We also used the India's own labor force survey from 2023 to 2024. And all of this was the data was measured and studied with analysis through Pearson correlation, one-way ANOVA, regression, and cross-tabulation. Now, the sample we collected initially was 248, but after removing inconsistent entries and data points, we came to a 169 sample, and government, education, and IT hold the most representative in the sample. And in terms of employment status, more than half, like 51%, were full-time employees, and the 29% student held the second most represent in the data set. And the response we got from the sample was overall that 35% of the respondents said that they work 40 hours, and more than half worked more than 50 hours, and that's considered overtime and not a reasonable hours worked. Apart from that, 67% of the respondents said that they ideally would want like a 40-hour a week schedule with 5 days per week working hours. And I think also considering the flexibility they would want from their work. So the first output kind of links the work-life balance, which mediates the hours and productivity link. We can see in the graph that the productivity kind of has a sharp decline after 48 to 50 hours, which kind of falls again to the point that the longer working hours do not equal higher productivity. And we can see that from the R being negative as well for the first one. The second finding that we had was higher work-life balance is equal to higher productivity, as we can see the R being positive there. Hours also reduce productivity even after controlling for work-life balance. And lastly, work-life balance was considered like the strongest predictor for productivity, not hours. And understanding that long hours erode well-being, and that erosion then hurts the productivity is the case that we're trying to make. In this graph, we can see India and China kind of log the most hours but the least output, and compared to Germany and Sweden, who log the fewest hours but the highest output. Output 3 kind of shows us, since we kind of looked at different sectors in India, the government sector logs in the highest hours and the lowest output, and also lowest productivity rating. This could be because of a lot of reasons, like bureaucratic processes or just the public sector itself. But yeah, I think the reform that we recommend later is much needed in the government sector than any other sector. We also used modeling and kind of understanding what actually drives productivity. Productivity was the outcome. We tested it with 3 predictors: working hours, work-life balance, and schedule flexibility. As we can see, working hours, the verdict came out significantly negative. Work-life balance was the strongest predictor for productivity, not the hours. And schedule flexibility was also very important, considering that employees who have control over their schedule actually report higher output and productivity. And this is all kind of visually being represented in the heat map there, which kind of shows that productivity and work-life balance and hours are kind of moving in opposite directions. Yeah, showing here. So coming to the key findings, overall, the research is trying to say that the working hours erode well-being, and it's the well-being that hurts productivity overall. Work-life balance and not hours drives output is the strongest predictor of productivity. Government sector definitely needs very structural reforms because highest hours are seen there, lowest productivity is seen there, and lowest well-being is also seen there. So all needs to be addressed together. India's productivity gap is structural. It's not the issue about effort. Since, as said, Germany works fewer hours and earns much more output. Lastly, awareness amongst workforce exists. 67% reject more hours, more output. 75% want equal or less than 40 hours per week. Same for wanting 5-day working week. 80% want more predictive and flexible work schedule as well. The role of AI is also important to consider, since a lot of organizations are adopting that, but it's important to implement it in a way that actually helps make the work lives of Indian employees better. Just the last few things: implications for organizations, shifting from hours logged towards more measurable output, enforcing flexibility and monitoring, capping overtime, and using AI for helping employees, not just putting more pressure on them. For policymakers, urgent public sector reform, as mentioned, government sector is really has a structural issue with productivity, and using pilot outcome-based systems could be using examples like Nordic and Iceland models. And it'd be also valuable to upgrade the national surveys, tracking hours, not just the jobs. For researchers, it would be valuable to use stratified national sampling to reduce the bias, the sampling bias that we have as a limitation, replacing self-reports with more objective metrics, applying more longitudinal design for establishing more cause and effect relationship, and isolating AI's impact to see both on hours and expectations. Unlike any other study, we also have limitations. The sample was not nationally representative. It was a moderately smaller sample, and government sector did have a higher share and may have skewed sector comparisons. Productivity is self-rated, hence social desirability bias couldn't be ruled out of the presentation. And the secondary data was average national figures, so variation couldn't be captured. Future scope, longitudinal study, as mentioned, using a higher sample size, objective performance rate, output volume, error rates could be used alongside self-report. And isolating AI as its own independent variable could be really helpful in measuring its effect on both hours and work-life balance. Extending the cross-national survey to replicate India comparisons with similar samples in Germany and China and Japan, and testing the work-life balance as a formal mediator using the structural equation modeling. Concluding with this, just want to say at the end, India does not have a work ethic problem. Indian employees do work as hard as almost everyone in the world. It is a more structural issue which needs to be prioritized. And yeah, because AI never sleeps, so someone has to make the case for rest, and that's why we're here. And that's it. Thank you so much for listening. And yeah, any questions? Should I just? Any questions? Yeah. Thank you.
Thank you, Shweta. Okay. Listen.
146.
146?
Yeah.
Yeah, I just opened it. Check it right. 146. There's a bill. That's a paper.
Shall I start?
Yes, wait. You want to start or you want to start? Can we let him start? You can start. Yes, when did you can start?
Okay, yeah, hi. So good afternoon, everyone, or good morning, based on whichever part of US you are in. I'm Gunjan Vasant Ramteke, presenting with co-author Rahul Modi. Today, we introduce UncertainNet, a Bayesian deep learning approach for calibrated liver fibrosis, staging from ultrasound designed for data scale clinical settings. Moving on to slide 2, which is we already there. Introduction. Liver fibrosis progresses silently into a cirrhosis and cancer if not caught early. B mode ultrasound is ideal screening tool, cheap, non-invasive, widely available, but staging is highly subjective. Deep learning models can automate this, but existing approaches have critical flaw. They give prediction with no confidence estimate. A model that's wrong and confident is clinically dangerous. UncertainNet solves this by combining Monte Carlo dropout with EfficientNet B3 to quantify uncertainty and when confidence is low. It routes the case to human expert instead of forcing a risky label. Moving on to slide 3. Can you move to slide 3? Yeah, thank you. So the related work here. Prior work progresses from handcrafted texture features to CNN transfer learning. VGG16, ResNet, DenseNet, EfficientNet, VIT, all achieving through AUC scores on fibrosis staging. However, none reported calibrated or uncertainty. The broader medical imaging literature confirms deep learning models are frequent overconfident. Our work bridges this gap by combining calibration, class imbalancing handling, and uncertainty based triage in one framework. We will move to the next slide, slide number 4, which speaks about the architecture. Slide number 4. Here, how uncertain networks. We use EfficientNet B3 as our feature extractor, followed by a Bayesian interference head where dropout stays active at interference time. We run T stochastic forward passes, each with different dropout mask, producing T predictions. This means gives our class estimate, the variance gives our uncertainty via predictive entropy. The key mechanism, if entropy exceeds threshold T, the model flags that case as uncertain and defers to human expert. The model knows what it doesn't know. For example, it always pushes to human at the end of the entire cycle. Moving on to slide number 5. Thank you. So what kind of data and training or methodology we used here? Just a second. Yes. We use liver histopathology, fibrosis, ultrasound images data set. So we have these different data sets, images, which we use for initial working. 5-class metaverse stagings were done, which was through F0 to F4. Images are usually, the way we did was 224 into 224. We split into 70, 15, 15 for train, validation, and testing. We applied class conditional augmentation and class weighted focal loss to handle natural imbalance in fibrosis data, because fibrosis data has this huge issues of a kind of natural imbalance when you are looking at those ultrasound images. So we did try different type of images. We did a split, and we trained it, validated, and tested. Slide number 6. Thank you. Yeah, so what were results after these data sets and training? The results, Uncertainty achieved 93.1 accuracy, which is super high. Macro F1 to 91.9%, and macro AUC was 0.978. The headline, the major headline, our expected calibrated error is just 0.0031 compared to baseline ranging from 0.087 to 0.112. That is a 3x improvement from the previous results. When our model says 90% confident, it's right 90% of the time. For triage at threshold t equal to 0.38, the model automatically handles 88.6 of the cases at 96.8% accuracy. The remaining 11.4% genuinely ambiguous are deferred to experts. Importantly, errors only occur between adjacent meta-wire stages, clinically reassuring since even pathologist struggles to distinguish neighboring stages. So what we're doing here, the results were basically calculated through our calibrations. Errors were super low, our confidence levels were super high, because we did see through different models, previous models, even pathologists had real big struggle identifying different stages just based on the images, and that's where our model comes into picture. This was the result. Moving on to slide number 7. This is more of a conclusion, what we concluded. This is important key takeaways from us, that confidence estimation is essential for clinical AI safety. This is a core of my research and also about this paper. Uncertainty achieves both high accuracy, reliable calibration. The triage gateway gracefully defers hard case rather than forcing risky predictions. Because the risky prediction in case of patients with clinical problem or clinical diseases could lead to death or more severe or more situations like death. So the triage gate gracefully defers hard cases rather than forcing risky prediction. So it defers it to the expert, basically human is what we're talking about. Future work includes multi-center validation, integration clinical variables, and federated learning. So this is what our next papers are going to be in future. So we do have references for the reviews. Yeah, that's all. Thank you.
Thank you so much. Thank you, Gunjan. Thank you, Rahul. With this, we have come to the end of this session. And thank you so much. Thank you so much to amazing session chairs. It was absolutely outstanding having you here. Thank you so much, all the presenters. And Momiji, if you're there, we can close the session now. This was the concluding presentation. Thank you, everybody. India team, thank you so much. All the IEEE members who are there watching. I know it is late night there, but still you are there on the system. Thank you so much. Thank you so much, everybody who joined.
Thank you to you too. Wonderful.
Thank you. Thank you so much, Dr. Gupta. Thanks so much. Good night, everybody. And good day, everybody here. Momiji, if you're there, you can close the session.
Okay, ma'am. Okay.
Thank you so much.